Hello there and welcome to Just About Earth, where curiosity slows down, science takes its time, and the distant past becomes a quiet place to wander through before sleep. Tonight, we're travelling far beyond written history, far beyond the first cities or even the first fires carefully tended by human hands. We're going back to a time when the world was louder with wind, heavier with heat, and filled with creatures that no longer walk the earth. And somewhere in that ancient landscape lived a being whose name is rarely spoken today. A member of our family tree that most people have never heard of, Homo Rudolfensis. It's a name that sounds technical, almost cold, the sort of label you might expect to find on a museum drawer or printed in small letters beneath a fossil behind glass. Yet behind that name was a living creature who woke each morning under a rising sun, who searched for food, who listened for danger in the tall grasses, who felt hunger and thirst and perhaps even a quiet flicker of curiosity about the world around them. Long before cities, before language as we know it, before anything we would recognise as civilization, there were lives unfolding in silence, lives that shaped what humanity would eventually become. And that brings a gentle question to mind, one worth asking before we go any farther. Where are you listening from tonight? Perhaps you're in a quiet room, or lying in bed, or sitting somewhere dimly lit while the world outside grows still. And what time is it for you right now? Late evening, perhaps, or the early hours of morning. It's a small thing to notice, but it's comforting to remember that while we're thinking about deep time measured in millions of years, each of us is still anchored in our own small moment, listening here, breathing slowly, letting the day drift away. If you find this journey peaceful, or interesting, or simply a gentle way to unwind, I'd be grateful if you gave the video a like and maybe subscribed. It helps this quiet little corner of science reach others who might enjoy a calm voice and a long walk through the past. And now, with that said, let's begin to wander. When most people think about human origins, a few familiar names tend to surface. Neanderthals, perhaps, maybe Homo erectus, or Lucy, the famous Australopithecus. But the deeper one looks into the fossil record, the more complicated the story becomes. The human family tree is not a straight line. It's a branching, tangled, sometimes confusing web of species that appeared, changed, overlapped, and disappeared across vast stretches of time. Some branches flourished for hundreds of thousands of years. Others flickered briefly and vanished, leaving behind only fragments of bone and a handful of questions. Homo Rudolfensis belongs to one of those quieter branches, not entirely forgotten by science, but certainly overshadowed by more famous relatives. To understand why, it helps to imagine the world as it was nearly 2 million years ago. The place is East Africa, a region that scientists often call the cradle of humanity. But it was not a cradle in the gentle sense of the word. It was a landscape shaped by tectonic forces, shifting climates, and ecosystems that changed over thousands of years. Lakes expanded and shrank. Forests gave way to open grasslands. Seasons brought drought, then rain, then drought again. Survival required flexibility, awareness, and a constant readiness to adapt. Picture a broad valley under a pale sky, the air warm, the horizon shimmering in the heat. Scattered acacia trees cast thin shadows across dusty ground. In the distance, herds of antelope move cautiously, ears flicking, always alert. Somewhere nearby, a predator watches, patient and silent, and moving through this landscape, upright, but not quite like us, are early humans, their bodies lean, their movements deliberate, their lives shaped by a world that offered no guarantees. These early humans were not alone. Multiple species of hominins lived in overlapping territories, each with slightly different adaptations, diets, and behaviours. Evolution, it turns out, often experiments with many variations at once. Some succeed, others fade away, and only in hindsight does the path to modern humans appear clear. Homo Rudolfensis was one of these experiments, What makes this species especially intriguing is that it doesn't fit neatly into the categories scientists once expected. For a long time, the story of human evolution was told as a simple progression. Primitive ancestors gradually becoming more human, step by step, species replacing species in an orderly march toward us. But fossils like those attributed to Homo Rudolfensis complicated that picture. They suggested that different kinds of early humans coexisted, each following its own evolutionary path, sometimes sharing the same landscapes, sometimes competing for the same resources. And that realization changed how we understand our origins. Instead of a single line, there was a mosaic of possibilities. Now, when we think about ancient humans, it's easy to imagine them as crude or simple, but that impression can be misleading. Even the earliest members of our genus were highly capable organisms, shaped by millions of years of natural selection. Their senses were sharp. Their awareness of their surroundings was constant. They knew the rhythms of the land, the patterns of animals, the locations of water, the signs of approaching storms. Life demanded attention, and attention was a skill they practiced every day. It's also worth pausing to consider how different their experience of time must have been. There were no clocks, no calendars, no schedules dividing the day into measured segments. Time was marked instead by sunlight and shadow, by hunger and rest, by the slow turning of seasons. Morning came when the sky brightened. Night arrived when darkness settled and the air cooled. The year unfolded in cycles of rain and dryness, abundance and scarcity. In such a world, awareness of the present moment wasn't something people had to practice. It was simply how life worked. And perhaps that's one of the quiet connections we can feel even now. When you slow down, when you listen to a steady voice or watch shadows move across a wall, there's a faint echo of that older rhythm, a reminder that the human mind evolved in environments where stillness and observation were essential. Returning to Homo Rudolfensis, one of the reasons this species captures the imagination is the mystery surrounding it. We know it existed. We have fossils that tell us something about its physical features, but many details remain uncertain, debated, or simply unknown. How did they live, exactly? How did they interact with other hominins? What did their voices sound like, if they had anything we would recognize as speech? Did they form bonds similar to ours, or did their social lives follow patterns now lost to time? These questions linger, partly because the fossil record is incomplete. Bones are fragile things. Most living creatures leave no trace at all after death. Fossilization requires a precise set of conditions: burial, mineralization, protection from erosion, and even then millions of years of geological change can scatter or destroy the evidence. So every fossil that survives is a rare survivor, a fragment of a story that might otherwise have vanished completely. Imagine for a moment how improbable it is that any trace of Homo Rudolfensis reached us at all. A skull, buried in sediment near an ancient lake, layers of earth slowly accumulating above it. Chemical processes replacing organic material with minerals, the shifting of continents, the rise and fall of climates, the passage of nearly 2 million years. And then, eventually, a group of scientists walking across a sunlit landscape scanning the ground, noticing something unusual in the dust, a curve of bone, a shape that doesn't belong to any modern animal, a discovery that opens a small window into a vanished world. But we're getting slightly ahead of ourselves because before that moment of discovery, there is another layer to this story worth exploring. The world itself, the environment that shaped these early humans long before anyone would ever give them a name. East Africa during this period was a place of change. Climate shifts caused forests to shrink in some regions and expand in others. Grasslands spread, lakes formed and disappeared. Animals migrated or adapted or vanished. For early humans, flexibility was not optional, it was survival. Some species adapted to open environments, developing bodies suited for long-distance walking. Others remained more closely tied to wooded areas. diets diversified. Tools in their earliest forms began to appear, simple stones shaped by deliberate strikes, sharp edges created not by accident, but by intention. And here, in these small acts, we see the beginnings of something profoundly human. The ability to reshape the environment, even in the simplest ways, to solve problems, to think ahead. Homo Rudolfensis lived during this period of transition when the genus Homo itself was still new, still experimenting with different forms and strategies. Their brains were larger than those of earlier hominins, though not yet approaching the size of modern humans. Their faces, as we'll eventually see, had features that puzzled scientists, neither fully primitive nor fully modern, but something in between, a reminder that evolution rarely moves in straight lines. What's especially fascinating is that for many years, some researchers weren't even sure whether Homo Rudolfensis was a distinct species at all. Fossils attributed to it were sometimes grouped with other early humans, particularly Homo habilis. Only later, after careful study and comparison, did differences begin to stand out, differences in skull shape, jaw structure, and proportions that suggested this was not simply a variation of a known species, but something separate, something deserving its own place in the human story. And that raises an interesting thought. How many other branches of our family tree existed, leaving behind no fossils at all? How many lives unfolded generation after generation without any trace reaching the present? The history we reconstruct is only a small fraction of what truly happened. Still, even fragments can tell remarkable stories. There's a certain quiet wonder in realizing that every human alive today carries within them a lineage stretching back through countless ancestors, through species whose names we know and others we never will, through landscapes and climates that no longer exist. Homo Rudolfensis is one of those distant relatives, separated from us by time so vast it's difficult to grasp, and yet connected by the unbroken chain of life. Long before the name Homo Rudolfensis appeared in textbooks, before debates filled scientific journals and museum displays were rearranged, there was only a vast stretch of land under an unforgiving sun, a shoreline that no longer exists, and a few people walking slowly across sediment that had been undisturbed for millions of years. The place was the eastern edge of a large lake in northern Kenya, known at the time as Lake Rudolph, a name given during the colonial era and later changed to Lake Turkana. Even today, it is an austere and striking landscape. The water often looks green or jade under the light, and the surrounding terrain can feel almost otherworldly, dry, wind-carved, and scattered with layers of ancient sediments exposed like pages of a book that has been left open for ages. For paleoanthropologists, however, this kind of landscape is not desolate at all. It is promising. Dry regions where erosion gradually strips away layers of earth can reveal fossils that would otherwise remain buried forever. The very harshness of the environment becomes an ally, patiently uncovering pieces of deep history. Expeditions to this region had already produced remarkable discoveries by the late 1960s and early 1970s. Fossil hunters knew that East Africa held clues to humanity's distant past, and teams returned season after season, enduring heat, dust, and long days of careful searching. The work itself was slow and methodical. Contrary to the dramatic scenes sometimes portrayed in films, discoveries rarely happen in sudden cinematic moments. More often, they begin with a trained eye noticing something small and unusual on the ground, a fragment of bone, a curve that doesn't belong to any modern animal, a texture that suggests mineralized tissue rather than ordinary stone. It takes patience to notice such details. Hours of walking, quiet concentration. The mind learns to filter patterns, to recognize shapes that others might overlook. And sometimes, after days of seeing nothing but pebbles and sediment, a single fragment appears that changes everything. In 1972 that fragment appeared. The fossil was discovered by Bernard Ngeneo, a member of a field team led by the well-known paleoanthropologist Richard Leakey. Ngeneo was experienced, observant, and familiar with the terrain. As he surveyed the area near Kubi Foro on the eastern side of the lake, he noticed pieces of a skull eroding out of the ground. Not just small fragments, but substantial portions, enough to suggest that something significant was buried there. Careful excavation began almost immediately. Fossils are delicate, and removing them requires meticulous work. Sediment must be brushed away slowly. Tools are used with precision, sometimes as gentle as dental picks or soft brushes. The surrounding rock is often left intact at first, forming a protective jacket around the fossil until it can be stabilized and transported. As more of the skull emerged, it became clear that this was not a minor find. The specimen, later catalogued as KNM-ER 1470, would become one of the most discussed fossils in the study of early humans. At first glance, the skull was striking. It was larger than expected for some of the early human species known at the time. The brain case suggested a cranial capacity significantly greater than that of many Australopithecines, those earlier hominins that walked upright but still retained many ape-like features. Yet the face was broad and somewhat flat, different from what scientists had seen in fossils attributed to Homo habilis. This combination puzzled researchers. The skull did not fit neatly into existing categories, and in science, when something doesn't fit, it often means there is something new to learn. Transporting the fossil from the field to the laboratory was only the beginning. Once in a controlled setting, specialists began the painstaking process of cleaning, reconstructing, and analysing the specimen. Fossils rarely emerge intact. Pieces must be aligned and joined. Missing sections must be inferred. Measurements are taken repeatedly to ensure accuracy. These early stages of study can take months or even years, and during that time, hypotheses begin to form. Scientists compare the fossil to others in museum collections, examining details of bone thickness, tooth size, jaw shape, and cranial proportions. Each feature becomes a clue. What made KNM-ER 1470 so intriguing was that its features seemed to challenge the prevailing narrative of human evolution. At the time, many researchers believed that early members of the genus Homo were relatively small-brained and gradually increased in brain size over time. Yet here was a skull that appeared older than some known Homo fossils, but with a surprisingly large brain case. Could this represent an entirely different lineage? Or was it simply variation within a known species? These questions sparked lively debate, the kind that unfolds slowly in academic papers, conferences, and long conversations among colleagues. Science rarely moves by sudden consensus. Instead, ideas are proposed, tested, challenged, and refined. For several years, the classification of the specimen remained uncertain. Some researchers argued it should be placed within Homo habilis. Others suggested it represented something distinct, a separate species that had lived alongside other early humans rather than evolving directly into them. Eventually the name Homo Rudolfensis was proposed, referencing the lake near which the fossil had been found. It was a way of acknowledging both the geographical origin and the uniqueness of the specimen. But naming a species does not end the discussion. In many ways, it begins a new one. Because fossils do not come with labels attached, every interpretation depends on evidence that is often incomplete. Additional discoveries are needed to confirm whether a species designation is truly justified. And in the case of Homo rudolfensis, more fossils were slow to appear. Years passed. Fieldwork continued. The landscape around Lake Turkana yielded other hominin remains, some of which appeared to share features with KNM-ER 1470. Gradually, a small but growing body of evidence suggested that this was not an isolated individual, but part of a broader population. Still, uncertainties remained. Some scientists questioned whether the differences between Homo rudolfensis and Homo habilis were significant enough to warrant separate species names. Others pointed out that variation within species can be substantial, especially over large geographic areas and long spans of time. This kind of debate is not a flaw in science, it is a strength. The willingness to question, to revisit assumptions, to refine classifications as new evidence emerges, this is how understanding deepens. Meanwhile, beyond the laboratories and journals, the fossil itself became something of an icon. Casts of KNM-ER 1470 appeared in museums around the world. Visitors looked at its broad face and large brain case, often surprised by how human it seemed in some ways, and how unfamiliar in others. There is something quietly powerful about standing before such a fossil. It is not just bone turned to stone, it is a reminder that the boundary between past and present is thinner than we sometimes imagine. The distance of nearly 2 million years feels immense, and yet the shape of a skull, the curve of a brow, the pattern of teeth, these are features we recognize, echoes of a shared ancestry. Returning to that day in 1972, it's worth imagining the scene once more, not as a dramatic revelation, but as a quiet moment in a long continuum of discovery. A person walking across an exposed hillside, a fragment of bone catching the light, a pause, a closer look, the realization that this was something unusual. No one present could have known exactly how significant the find would become. That understanding came later, gradually, as evidence accumulated and interpretations evolved. And the landscape itself, the sediments around Lake Turkana, holds many more stories still buried. Each layer represents a different period in the past, a different environment, a different community of plants and animals. Fossils of ancient elephants, crocodiles, antelope and fish lie preserved alongside those of early humans, creating a record not just of individual species, but of entire ecosystems. Reconstructing those ecosystems is another careful process. Scientists study pollen grains trapped in sediments, isotopes in fossil teeth, the shapes of ancient river channels. From these clues, they can infer whether the region was wetter or drier, more forested or more open, whether grasses dominated or shrubs and trees. And these details matter because the environment shapes evolution. The availability of food, the presence of predators, the stability or instability of climate, all influence which traits become advantageous and which do not. For Homo Rudolfensis, the world around Lake Turkana was likely a mosaic of habitats, patches of woodland, open grasslands, lakeshores rich with resources. Such diversity would have favoured flexibility, the ability to exploit different foods, to move across varying terrain, to adapt as conditions changed. Yet even as we piece together this picture, many aspects of their lives remain beyond our reach. We do not know what their voices sounded like, whether they used gestures to communicate, how they cared for their young, or what fears stirred them in the dark. The fossil record preserves bones, not thoughts, not memories, not dreams. Still, there is a certain comfort in knowing that these distant relatives existed, that they navigated a world both harsh and beautiful, that their lives, though silent to us now, were once as immediate and vivid as our own. And the discovery at Lake Rudolph was not just the uncovering of a skull, it was the opening of a window, small but clear, into that vanished world. As researchers continued to study the fossils, another question gradually came into focus, one that would shape decades of discussion. What exactly defines a species within the human lineage? How different must two populations be before we consider them separate? And how do we make that judgment when all we have are fragments of bone scattered across time? At first, the skull did not seem like a revolution. It was simply another fossil among many, another specimen carefully cleaned, measured and compared in the quiet rooms where paleoanthropologists spend so much of their time. Yet the longer scientists studied it, the more it resisted easy explanation. It did not behave, in a scientific sense, the way it was expected to behave. And sometimes, in science, the most important discoveries are not the ones that confirm what we believe, but the ones that quietly refuse to fit. To understand why this skull caused so much discussion, it helps to remember what researchers thought they knew about early humans in the early 1970s. The prevailing picture was relatively straightforward. Australopithecines, smaller-brained and more ape-like, were believed to have gradually given rise to early members of the genus Homo. Those early humans, represented by fossils attributed to Homo habilis, were thought to show modest increases in brain size and somewhat more refined features. The story was often imagined as a kind of steady progression, step by step, from primitive to more advanced. It was a neat and satisfying narrative, perhaps a little too neat. When KNM-ER 1470 was reconstructed and examined in detail, several features stood out immediately. The brain case was larger than expected, suggesting a cranial capacity that rivaled or even exceeded that of some specimens classified as Homo habilis, yet the face was broad and flat in ways that differed from other early Homo fossils. The jaw was robust, the teeth relatively large, and the overall proportions did not match the tidy sequence many researchers had anticipated. In simple terms, the skull seemed to combine traits in an unexpected way. Some features looked more advanced, others more primitive, and the pattern did not align with the assumed timeline. This was not merely a matter of minor variation. Variation within species is common, of course. No two individuals are identical. But scientists rely on patterns across multiple fossils to identify consistent differences that suggest separate populations or lineages. The question was whether KNM-ER 1470 represented such a difference, or whether it was simply an unusual individual within a known species. Answering that question required patience and a great deal of careful comparison. Researchers began by examining the skull in the context of other fossils from East Africa. Measurements were taken repeatedly, distances between landmarks on the bone, angles of the facial structure, the shape of the eye sockets, the curvature of the cranium. These details may sound dry, but they are the language of paleoanthropology. Each measurement is a clue, a piece of evidence that can be compared across specimens. What emerged from these comparisons was a growing sense that this skull did not comfortably belong with Homo habilis. The differences were not limited to a single feature, but appeared across several aspects of anatomy. The face was broader. The palate, the roof of the mouth, was wider. The brain case had a distinct shape. Taken together, these traits suggested that this was not simply variation within a species, but something more. And yet science rarely moves quickly when it comes to rewriting established ideas. Skepticism is part of the process. Some researchers argued that the reconstruction of the skull might have introduced distortions. Fossils often require reconstruction from fragments, and slight differences in alignment can affect measurements. Others suggested that sexual dimorphism, differences between males and females of the same species, might explain the unusual features. These were reasonable possibilities, and they were taken seriously. Additional analyses were conducted, reconstructions were revisited, new fossils were examined as they were discovered. Slowly, the weight of evidence began to shift. What made the situation particularly intriguing was that KNM-ER 1470 was not alone. Other fossils from the same region, including fragments of jaws and teeth, appeared to share similar characteristics. These pieces, scattered across different excavation sites and layers of sediment, hinted at a population rather than a single anomalous individual. And populations, in evolutionary terms, tell stories. If a consistent pattern of anatomical features appears across multiple individuals from the same period and region, it becomes increasingly difficult to dismiss those differences as coincidence or variation. Instead, scientists begin to consider the possibility of a distinct species, one that lived alongside others rather than replacing them in a simple sequence. This realization was part of a broader shift in paleoanthropology. By the late 20th century, researchers were beginning to understand that human evolution was far more complex than a straight line. Multiple hominin species often coexisted, occupying overlapping territories and perhaps interacting in ways we can only imagine. The skull from Lake Rudolph became one of the key pieces of evidence supporting this more intricate view of our past. There was also something quietly humbling about this discovery. For decades, the fossil record had been interpreted through the lens of limited evidence. Each new find had the potential to reshape the entire narrative, not because earlier scientists were careless, but because the record itself is fragmentary. Understanding deep time is like assembling a vast puzzle in which most of the pieces are missing, and sometimes a single piece forces you to reconsider how the rest of the puzzle fits together. It's worth pausing for a moment to think about what a skull actually represents. Not just bone, but the framework of a living being's face. The structure that once held eyes that watched the landscape, a mouth that chewed food gathered from the land, a brain that processed sensations, memories, perhaps even simple forms of planning or anticipation. When scientists measure a fossil skull, they are not only studying anatomy, they are trying to infer aspects of a life, how that individual moved, what they might have eaten, how they interacted with their environment. The broad face of KNM-ER 1470, for instance, suggests powerful chewing muscles and a diet that may have included tough or fibrous foods. The size of the brain case hints at cognitive capacities that were developing along new lines, not yet modern, but moving in that direction. These interpretations are cautious, always provisional, but they help bring the fossil to life, not as a static object but as part of a dynamic ecosystem. There is also an emotional dimension to such discoveries, though scientists rarely speak of it in formal papers. To hold a fossil in your hands, to realise that this bone belonged to a being who lived nearly 2 million years ago can be a profoundly moving experience. It creates a sense of continuity, a quiet awareness that the boundary between past and present is less absolute than it seems. Every human alive today is connected through countless generations to individuals like the one whose skull was found near Lake Rudolph. The connection is unimaginably distant in time, yet biologically unbroken. As debates about classification continued, the name Homo Rudolfensis gradually gained acceptance, though not without ongoing discussion. Some researchers still prefer to group these fossils within Homo habilis, emphasizing the uncertainties involved. Others maintain that the differences are significant enough to justify a separate species. This kind of disagreement is not unusual in paleoanthropology. Species boundaries in the fossil record are often difficult to define, especially when dealing with populations that lived hundreds of thousands of years apart and left behind only partial remains. In a sense, the skull that didn't fit the story became a reminder that the story itself was still being written. And beyond the scientific debates, the discovery had a broader impact on how people think about human evolution. It encouraged a shift away from viewing our ancestry as a ladder of progress and towards seeing it as a branching tree, or perhaps even a braided river, with multiple channels flowing simultaneously, some merging, some ending, some continuing in unexpected directions. Homo Rudolfensis represents one of those channels, a lineage that existed, adapted, and eventually disappeared, leaving behind only fragments to mark its passage. The disappearance itself is another mystery. The fossil record suggests that this species lived roughly between 2.4 and 1.8 million years ago, overlapping in time with other early humans. Why it vanished while other lineages persisted is not entirely clear. Climate changes, competition, dietary shifts, or a combination of factors may have played a role. Extinction, after all, is the rule rather than the exception in the history of life. Most species that have ever lived are gone. Survival is rare, and the survival of our own lineage was far from inevitable. Reflecting on this can bring a certain perspective. The modern world often feels fast and urgent, filled with deadlines and schedules, but the deeper history of our species unfolds on a scale so vast that individual lifetimes become almost immeasurably small. And yet, those lifetimes matter, just as the life of the individual whose skull became KNM-ER1470 mattered, even though their name, their voice, their thoughts are lost to us. What remains is the shape of bone, the silent testimony of existence. As more fossils were discovered in the decades that followed, the picture of early Homo became richer and more complex. Researchers began to recognize that diversity, not uniformity, was the defining feature of this period. Different species experimented with different ways of living, different diets, different strategies for survival. Some were more specialized, others more flexible. Some left descendants, others did not. When scientists look at fossils like these and try to classify them, what exactly are they looking for? What defines a species, especially when the evidence comes not from living populations, but from scattered bones buried in ancient sediments? Deciding what makes a species human sounds at first like it should be simple. After all, we know what a human looks like, don't we? We see faces every day, hear voices, watch people move through the world with intentions and thoughts and emotions. It feels obvious. And yet when scientists try to answer that same question, while looking at fragments of bone buried for nearly 2 million years, the answer becomes far less clear. A skull, a jaw, a few teeth, sometimes only a portion of a limb, these are often the only clues available. From such limited evidence, researchers must determine not only what an individual looked like, but whether that individual belonged to a known species, a variation of one, or something entirely different. It is a careful, sometimes uncertain process, and it forces scientists to confront a deeper question. What does it actually mean to be human? One way to begin answering that is to look at how species are defined in general. In biology, a species is often described as a group of organisms capable of interbreeding and producing fertile offspring. That definition works well for living animals, where behaviour and reproduction can be observed. But for extinct species, especially ones separated from us by millions of years, it becomes impossible to apply directly. No one can observe mating patterns or genetic compatibility in the fossil record, so paleoanthropologists rely on anatomy instead. They examine physical traits, the shape of the skull, the size and arrangement of teeth, the structure of the pelvis, the proportions of the limbs. Patterns across multiple individuals help reveal whether a population shares consistent features distinct from others. In the case of early humans, certain traits have traditionally been associated with the genus Homo. A larger brain relative to body size is one of them. Changes in the structure of the face, often becoming flatter and less projecting than in earlier hominins, are another. Teeth tend to become smaller, especially the molars and canines, reflecting shifts in diet and food processing. The hands show adaptations for precise grip, suggesting increasing tool use. The legs and feet indicate efficient upright walking over long distances, yet none of these traits appeared all at once. Evolution rarely works in sudden leaps. Instead, features accumulate gradually, sometimes appearing in one lineage but not another, sometimes reversing, sometimes persisting for long periods in unexpected combinations. This is why fossils like those attributed to Homo Rudolfensis are so fascinating. They display a mixture of traits. The brain case is relatively large, suggesting cognitive changes underway, but the face and teeth retain features that seem more primitive, more similar to earlier hominins. It is a reminder that evolution does not follow a checklist. There is no single moment when a species suddenly becomes human. There is also the question of behaviour. When people think about what makes us human, they often point to language, culture, art, or complex tools. These are indeed defining aspects of modern humanity, but they leave little trace in fossils, especially in periods as remote as 2 million years ago. Stone tools, when preserved, provide some clues. The earliest known tools date back more than 3 million years, even before the emergence of the genus Homo. By the time Homo Rudolfensis lived, simple stone tools were already part of the landscape. These tools were not sophisticated by later standards, but they required planning and coordination, selecting suitable stones, striking them at the right angle, producing sharp edges for cutting. The presence of tools suggests cognitive abilities beyond those of earlier primates. It indicates foresight, problem-solving, and perhaps even teaching, since tool-making techniques likely had to be learned and passed on. Still, tool use alone does not define humanity. Some modern animals use tools as well, certain birds, sea otters, chimpanzees. The difference lies not only in the tools themselves, but in the cumulative nature of human culture, the way knowledge builds over generations. That kind of cultural accumulation leaves faint traces in the deep past, making it difficult to pinpoint exactly when it began. Another trait often associated with humanity is social complexity. Humans are intensely social creatures. We form families, communities, and networks of cooperation. We share food, care for the sick, and communicate intentions through gestures and expressions. These behaviours leave only indirect evidence in the fossil record, but certain clues exist. For example, the survival of individuals with healed injuries suggests that others provided care during recovery. The distribution of fossils at certain sites hints at group living or repeated use of particular locations. Cut marks on animal bones indicate coordinated scavenging or hunting. Whether Homo Rudolfensis displayed such behaviours in a way comparable to later humans is difficult to say with certainty, but it is reasonable to imagine that some level of cooperation existed. Survival in the environments of East Africa would have been challenging for solitary individuals. Groups offered protection, shared knowledge of resources, and assistance in raising young. It is also worth considering the role of the environment in shaping what we think of as human traits. Many characteristics we associate with humanity, upright walking, endurance, flexibility, and diet, likely evolved in response to changing climates and landscapes. As forests gave way to more open environments, the ability to travel long distances efficiently became advantageous. As food sources varied, adaptability became essential. In this sense, humanity is not a fixed set of traits but a dynamic process, a way of living that emerged gradually as our ancestors interacted with their surroundings. There is a quiet humility in recognizing this. The qualities we often see as uniquely human did not appear suddenly or fully formed. They were shaped over millions of years, through countless small changes, each one subtle, each one building on what came before. Returning to the question of species classification, scientists must weigh all these factors: anatomy, environment, behavior, inferred from tools and fossils, patterns of variation across populations. And even then, conclusions remain provisional. New discoveries can reshape the picture at any time. The boundaries between species, especially in the human lineage, are often blurred. Populations may have interbred. Traits may have overlapped. Evolution does not produce neatly separated categories. It produces gradients, transitions, and diversity. Homo Rudolfensis occupies one of those transitional spaces. Its features suggest a species that was part of the early radiation of the genus Homo, experimenting, adapting, finding its place in a changing world. Whether it represents a direct ancestor of later humans or a side branch that eventually vanished is still debated. But perhaps that distinction matters less than it might seem. Even side branches contribute to the broader story. They reveal the range of possibilities evolution explored, the different ways early humans adapted to similar challenges. And there is something deeply reassuring in this broader view. It reminds us that humanity is not the result of a single inevitable path, but of many intersecting histories, many experiments in survival, many lives lived under ancient skies. It also invites us to reconsider how we define ourselves. If being human is not simply a matter of brain size or tool use or facial structure, what is it? Is it awareness, the capacity to reflect, to imagine the past and future? Is it empathy, the ability to care for others? Is it curiosity, the urge to explore and understand? These qualities are difficult to measure in fossils, yet they feel central to our identity. And perhaps that is part of the answer. Humanity is not defined by a single trait, but by a constellation of them, biological, behavioural and cultural, all emerging gradually over time. When scientists look at a fossil skull and ask whether it belongs to a human species, they are not only making a technical classification, they are tracing the roots of what we are, following the threads of a story that stretches back millions of years. If we want to understand Homo Rudolfensis, it helps to step even farther back than the fossils themselves, to look at the stage on which this story unfolded. Because no species exists in isolation, every organism is shaped, quietly and persistently, by the land beneath its feet, the climate above its head, and the living community around it. To imagine East Africa roughly 3 million years ago is to enter a world both familiar and profoundly different, a landscape that already contained the roots of the environments we know today, yet still carried traces of older, vanished ecosystems. The first thing to picture is movement. Not the movement of animals or people, but the movement of the earth itself. East Africa sits along one of the most remarkable geological features on the planet, the East African Rift System. This vast region is slowly pulling apart as tectonic plates drift, creating valleys, volcanoes and basins that reshape the land over immense spans of time. Even now, the process continues, though far too slowly for us to notice in a single lifetime. 3 million years ago, this rifting had already created a landscape of long valleys bordered by higher ground, dotted with lakes that formed in low-lying basins. Some of these lakes lasted for thousands of years before shrinking or vanishing. Others grew and connected during wetter periods, forming large inland seas. Shorelines advanced and retreated. River channels shifted. Layers of sediment accumulated, preserving the remains of plants, animals and early humans who lived nearby. These sediments would one day become the fossil-rich deposits that scientists study today, but at the time they were simply mud, sand and silt carried by water and wind, settling quietly year after year. The climate of East Africa during this period was not constant. It changed in cycles influenced by variations in Earth's orbit, shifts in ocean currents, and the gradual rise of mountain ranges that altered patterns of rainfall. Some centuries were wetter, with expanded forests and plentiful water. Others were drier, with grassland spreading and lakes shrinking. These fluctuations were not abrupt disasters, but slow transformations, unfolding over generations. For the creatures living there, adaptability was essential. If you were standing in that landscape at sunrise, the air would likely feel warm even in the early hours. Mist might linger near the water's edge, and the calls of birds would carry across the open ground. Herds of grazing animals would already be moving, feeding in the cooler part of the day before the heat intensified. The diversity of animals in East Africa at that time was remarkable. Many species would look familiar in outline, though not always identical to those alive today. There were ancient relatives of elephants, some with tusks arranged in ways that might seem unusual to modern eyes. There were antelope of many kinds, adapted to different habitats, some built for speed across open plains, others suited to browsing in wooded areas. There were giraffes, though not all shaped exactly like the ones we recognise now. There were pigs, horses, and large cats, each filling a particular role in the ecosystem. Predators were a constant presence. Saber-toothed cats moved through patches of cover, relying on stealth and sudden bursts of speed. Hyena-like carnivores scavenged and hunted. Crocodiles lurked in rivers and lakes, patient and nearly invisible until the moment of attack. For smaller animals, and for early humans, awareness was a matter of survival. The vegetation varied across the region. In some areas, woodland dominated, with clusters of trees providing shade and food. In others, open grasslands stretched to the horizon, broken only by scattered shrubs and the occasional tree. Near water sources, denser vegetation thrived, attracting animals that came to drink or feed. This mosaic of habitats was important. It created opportunities for species that could move between different environments, exploiting varied food sources and adjusting their behavior as conditions changed. Early humans, including the ancestors of Homo Rudolfensis, were among those flexible species. Walking upright, which had begun evolving millions of years earlier, offered advantages in such landscapes. It allowed individuals to see over tall grasses, to travel efficiently across long distances, and to carry food or tools. But upright walking also came with trade-offs. The human spine and hips evolved gradually, and early hominins still retained some features suited for climbing or moving through trees. This combination suggests that many early humans were not confined to a single habitat. They likely spent time both on the ground and in wooded areas, moving as needed in search of food and safety. Food itself came in many forms. Fruits, leaves, seeds, roots, and tubers were important resources. Insects provided protein. Occasionally meat was obtained, perhaps through scavenging or opportunistic hunting. The exact balance of these foods varied by species and environment, and it likely changed from season to season. Finding food required knowledge, the ability to remember where certain plants grew, when fruits ripened, where animals gathered, and which water sources remained reliable during dry periods. This kind of knowledge was not written down or spoken in the ways we understand today, but it was learned, remembered, and shared within groups. And that sharing may have been one of the most important developments in human evolution. It is easy to underestimate how much information a landscape contains. To an unfamiliar observer, a patch of ground might look uniform, but to someone who knows the area well, it holds countless clues: tracks in the soil, broken branches, changes in the colour of vegetation, distant sounds that signal the presence of animals or people. Early humans would have been skilled observers, attentive to details that meant the difference between hunger and nourishment, danger and safety. Another aspect of East Africa at this time was the presence of volcanoes. The Rift Valley region has long been geologically active, and volcanic eruptions occasionally spread ash across wide areas. While such events could be destructive in the short term, they also played a role in preserving fossils. Layers of volcanic ash can cover remains quickly, protecting them from scavengers and decay, and later hardening into rock that preserves bones for millions of years. In a quiet way, these eruptions contributed to the record that allows us to reconstruct the past today. Water, as always, was central to life. Lakes and rivers attracted animals of every kind, creating gathering points where interactions occurred, some peaceful, some not. For early humans, these areas offered both opportunities and risks. Water meant food and hydration, but it also meant predators. It is likely that groups approached such places cautiously, watching, listening, perhaps waiting until larger animals had moved on before stepping forward. The rhythm of the day would have been governed by temperature and light. Activity in the early morning and late afternoon, rest during the hottest hours, and a retreat to safer locations as darkness approached. Night brought its own challenges. Without fire, which would not become a regular part of human life until much later, early humans relied on vigilance and group cohesion to reduce the risk of predation. The night sky, however, would have been astonishingly clear, unpolluted by artificial light. Stars spread across the darkness in numbers difficult to imagine today. Whether early humans noticed or cared about the patterns above them is something we cannot know, but the sky was always there, vast and steady, marking the passage of time in ways both subtle and profound. Generations lived and died under that sky, their lives measured not in years as we count them, but in cycles of seasons, in the growth of children, in the memory of rains and droughts. The landscape itself was not static over the span of centuries. Lakes expanded and contracted, grasslands shifted, forest patches appeared and disappeared. Animals migrated in response to these changes, and early humans moved as well, following resources, exploring new areas, adapting to new conditions. Adaptation was not a conscious strategy, but a gradual process shaped by natural selection. Individuals with traits suited to the changing environment were more likely to survive and pass on those traits. Over many generations, populations changed, sometimes subtly, sometimes in more noticeable ways. Homo Rudolfensis would emerge within this dynamic setting, shaped by pressures that favoured flexibility in diet, movement, and social behaviour. Their story cannot be separated from the story of the land itself. There is also something quietly grounding in realising how long these processes unfolded. 3 million years is a span so vast that it stretches the imagination. Entire mountain ranges have risen and eroded in less time. Rivers have carved valleys and changed course countless times. Species have appeared, flourished, and vanished. And yet, in that immense expanse, there were individual days, ordinary days, mornings when the sun rose over the Rift Valley, when early humans woke, stretched, and began the familiar work of finding food and avoiding danger. Lives that felt immediate and present to those living them, just as our own lives feel immediate to us now. Thinking about this can shift one's sense of scale in a calming way. The urgency of modern life, the constant movement of clocks and schedules, fades a little when set against the slow rhythms of geological time. Still, the world of 3 million years ago was not peaceful in the way we might imagine. It was demanding. Survival required attention, cooperation, and resilience. Droughts could last for years. Food sources could fail. Predators were never far away. And yet, life persisted, adapting again and again, exploring new possibilities, branching into new forms. Among those forms were the early members of the genus Homo, including the lineage that would one day be called Homo Rudolfensis. They did not know they were part of an unfolding story. They simply lived, day by day, within the limits and opportunities of their world. As time passed and climates continued to shift, the landscapes around lakes like Turkana would change further, creating conditions that shaped the evolution of multiple hominin species. Some would develop larger brains, new tool-making techniques, and broader ranges. Others would remain more specialised, tied to particular environments. Seen from a distance, the region where Homo Rudolfensis lived might have looked calm, almost timeless. A wide basin of shimmering water bordered by low hills and scattered trees. But a closer look would have revealed a landscape in constant motion, not in the dramatic sense of earthquakes or storms every day, but in slower, quieter ways. Shorelines crept forward or retreated as seasons changed. Vegetation shifted in response to rainfall. Herds moved across the plains, followed at a distance by watchful predators. Nothing remained exactly the same for long. The lakes themselves were the anchors of this environment. Large bodies of fresh water gathered in the basins formed by tectonic activity, fed by rivers and seasonal rains. Some lakes lasted for thousands of years, stable enough that generations of animals and early humans came to depend on them. Others shrank or vanished as climates changed, leaving behind mineral deposits and layered sediments that would one day harden into stone. For Homo Rudolfensis, lakes were both opportunity and risk. Water meant life. Plants grew more densely along the shores. Fish and shellfish could sometimes be gathered in shallow areas. Animals of every size came to drink, from small antelope to enormous elephants. Where animals gathered, food could sometimes be found, whether in the form of prey, scavenged remains, or edible plants that thrived in moist soil. But where animals gathered, predators were never far away. To approach a lakeshore required caution. Early humans likely paused often, scanning the ground and the waterline, listening for sudden movement. Crocodiles were especially dangerous, silent and nearly invisible in the shallows. A single careless step near the edge of the water could be fatal. Large cats also patrolled these areas, taking advantage of the predictable movements of prey. It is easy to imagine a small group of Homo Rudolfensis approaching the water at dawn, when the air was cooler and visibility was good. They would not have walked casually. Their movements would have been alert, deliberate, heads turning, ears tuned to every sound. Survival favoured those who noticed small changes in their surroundings, a ripple on the water, the sudden flight of birds, the silence that sometimes falls when a predator is near. Away from the lakes, the land changed character. In some areas, open grasslands stretched for kilometres, dotted with shrubs and the occasional tree. These plains supported grazing animals in large numbers. Herds moved slowly as they fed, their paths shaped by the availability of grass and the presence of water. Grasslands offered visibility, which was both an advantage and a disadvantage. Predators could be seen from a distance, but so could anything else moving across the open ground. Early humans crossing such areas were exposed, and it is likely they preferred to travel along the edges of different habitats, where trees or uneven terrain provided some cover. Wooded areas formed another important part of the landscape. These were not dense forests in most places, but clusters of trees interspersed with open ground. Shade made these areas more comfortable during the hottest hours of the day. Fruits, leaves, and insects provided food. Branches offered refuge, especially for younger or smaller individuals who could climb more easily. Climbing was still a useful skill for many early hominins. Although they walked upright, their anatomy suggests they retained some adaptations for moving in trees. Long arms and curved finger bones seen in related species indicate that the boundary between ground and canopy was more fluid than it is for modern humans. Sleeping in trees or in sheltered areas may have reduced the risk of nighttime predation, though it would not have eliminated it entirely. Large predators were capable climbers, and snakes posed their own dangers. Night, in that world, belonged mostly to creatures with sharper teeth and better vision in the dark. During the day, the sounds of the landscape would have been constant but varied. Insects buzzing in the heat, birds calling to one another across distances, the low rumble of distant animals moving through brush, the splash of something entering water, the wind moving through grasses producing a steady whispering sound. For early humans, these sounds were not background noise, they were information. A sudden change in the usual pattern could signal danger or opportunity. A herd approaching might mean a chance to scavenge after predators had fed. The alarm calls of birds or monkeys might indicate a stalking carnivore. Listening, in such an environment, was a survival skill as important as vision or strength. The forests, where they were denser, supported different kinds of life. Primates moved through the branches, feeding on fruits and leaves. Small antelope browsed among the undergrowth. Birds nested in thick foliage. These areas were cooler, often more humid, and the ground was softer underfoot, covered with fallen leaves and organic debris. Food sources in wooded areas could be more predictable than in open plains, but they were also more scattered. A group might spend hours moving from one fruiting tree to another, gathering what they could, always aware that other animals competed for the same resources. Competition was a constant presence, not only from predators, but from other herbivores and omnivores. Baboons, for example, were widespread in many parts of Africa and were intelligent, adaptable, and often aggressive. Encounters between early humans and such animals could have been tense, especially when both sought the same food. The rhythm of the season shaped all of this. During wetter periods, grasses grew taller and greener, lakes expanded and food was more abundant. Animals dispersed more widely, and the landscape felt, in a sense, more forgiving. In drier times, conditions became harsher. Water sources shrank, vegetation thinned, herds concentrated near remaining lakes and rivers, increasing competition and attracting more predators. For early humans, these periods required greater movement, longer journeys in search of food, and careful management of energy. Energy was a precious resource. Every step taken, every climb, every moment of alertness required calories. Finding food was not simply a matter of preference, but of necessity. A successful day meant enough to eat, perhaps some surplus shared within a group. An unsuccessful day meant hunger, and repeated hunger weakened individuals, making them more vulnerable to illness, injury and predation. Weather also played its part. Rainstorms could arrive suddenly, drenching the ground and filling dry channels with rushing water. Lightning struck trees. Winds swept across open areas, carrying dust or the scent of distant fires started by natural causes. Temperature changes between day and night could be significant, especially in more elevated areas. All of these factors created a world that demanded awareness and flexibility. Predators, of course, were among the most powerful influences on behaviour. Saber-toothed cats, some larger than modern lions, were formidable hunters. They relied on ambush, using cover and patience to approach their prey. Hyenas and other scavengers followed, capable of crushing bone with powerful jaws, leaving little behind. For Homo Rudolfensis, avoiding predators was likely a daily concern. Groups may have stayed together for safety, relying on multiple pairs of eyes and ears to detect danger. Simple vocalizations or gestures could have been used to signal warnings. Even without language as we know it, communication would have been essential. Fire, which would later become a transformative tool for human ancestors, was probably not yet under regular control at this time. Without fire, nights were darker, colder, and more dangerous. Darkness limited movement and activity, encouraging rest and stillness. Rest itself was not always peaceful. Sleep in such an environment would have been light and easily disturbed, shaped by sounds in the darkness and the need to remain ready to wake quickly. Yet despite all these challenges, this landscape was not only harsh, it was also rich with life and possibility. Sunrises over the lakes would have been beautiful in a simple, immediate way, light spreading across water, birds lifting into the air, the temperature rising slowly. Evenings brought cooler air and long shadows, a time when many animals became active again, and the sky deepened toward night. These cycles repeated day after day, season after season, forming the background of countless lives lived without written records or lasting monuments. In such a world, learning was continuous. Young individuals watched older ones, observing how to find food, how to recognize edible plants, how to move quietly, how to respond to danger. Knowledge was not stored in books, but in memory and practice, passed from one generation to the next through example. This transmission of knowledge, even in its simplest form, was a powerful force. It allowed groups to adapt more quickly than species relying solely on instinct. Behaviours refined over time could improve survival, even if only slightly, and small advantages, repeated over many generations, can shape the course of evolution. Homo Rudolfensis lived within this intricate web of relationships, with the land, with animals, with one another. Their lives were not easy, but they were not merely a struggle either. There would have been moments of rest, of quiet, of social interaction within groups, grooming, sharing food, perhaps simple forms of play among the young. These small moments, rarely preserved in the fossil record, were part of what it meant to be alive in that time and place. Morning in the world of Homo Rudolfensis did not begin with alarms, schedules, or glowing screens. It began with light. The first pale brightness spread slowly across the horizon, and with it came a subtle change in temperature, a faint stirring of birds, the distant movement of animals beginning their day. For a small group of early humans resting in a sheltered place, perhaps among low trees or near a rocky rise, this light was the quiet signal that another day of survival was beginning. Waking was not sudden. It was gradual, shaped by the sounds and sensations of the environment. Someone shifted, another stirred, eyes open to the changing sky. There would have been no spoken good mornings, at least not in the way we understand language today, but there were likely soft vocalizations, movements, glances, small acknowledgements of presence that reinforced the bonds of the group. Groups were essential. A solitary individual in that landscape faced overwhelming risks. Together, early humans could watch for predators, share food, and care for the young. Cooperation, even in simple forms, increased the chances of survival. After waking, the first task was often to assess the surroundings. Was there danger nearby? Were predators moving in the distance? Were other groups of animals approaching the water or grazing grounds? Observation came before action. Hunger was a constant companion. The body does not store large reserves of energy without regular access to abundant food, and for early humans, each day required effort to secure enough to eat. There was no certainty that food would be found quickly. Some days brought success, others demanded long hours of searching. Movement began early, for the heat of midday. The group would travel together, scanning the ground and vegetation. Edible plants formed a large part of the diet. Tubers hidden beneath the soil could be dug out with sticks or stones. Fruits, when available, were valuable sources of energy. Seeds and nuts required patience to gather and sometimes skill to open. Insects were another important resource, often overlooked in modern imagination but rich in protein. Termites, grubs, and other small creatures could be collected by breaking open nests or turning over logs and stones. Occasionally, opportunities for meat appeared. Large predators often left behind remains after feeding, and early humans may have scavenged these carcasses, using simple stone tools to cut away pieces of flesh or crack bones for marrow. This required caution. Returning predators, competing scavengers, or aggressive animals could pose serious threats. Stone tools, though simple, played a quiet but significant role in daily life. A sharp edge created by striking one stone against another could slice through tough materials far more effectively than teeth or fingernails alone. Such tools were not carried in large collections or stored for long periods as far as we know, but individuals may have kept useful stones and reused them when possible. The act of making a tool required attention and practice. Selecting the right kind of stone, striking at the correct angle, and producing a usable edge were skills learned over time. Watching and imitating others was likely the primary way knowledge spread within a group. As the sun rose higher, temperatures climbed. The heat of East Africa could become intense, and activity often slowed during the middle of the day. Groups may have sought shade beneath trees or in the shelter of rocks. Rest during these hours conserved energy and reduced the risk of overheating. Rest did not mean sleep in the deep sense, but a period of relative stillness. Individuals groomed one another, removing dirt or insects from hair and skin, a behaviour seen in many primates, and one that strengthened social bonds. Young individuals played, testing their strength and coordination, learning through movement and imitation. Social interactions, though silent to us now, were likely rich in meaning. Gestures, facial expressions, and simple vocal sounds could convey intentions, warnings, or reassurance. Communication did not require complex language to be effective. Afternoons often brought renewed activity as the heat began to ease. Movement resumed, sometimes toward water sources. Drinking required caution, as predators often waited near lakes and rivers. Approaching the water in small groups, scanning constantly, and retreating quickly if danger appeared would have been common behaviour. Water was essential not only for drinking, but also for cooling the body. On especially hot days, standing in shallow water for brief periods might have provided relief, though always with vigilance. Children, as in all human societies, required care and protection. They were vulnerable, slower, less experienced. Adults likely kept them close, guiding them, teaching them what to eat and what to avoid, how to recognize danger, how to move quietly. Learning in such a world was practical and immediate. Knowledge had direct consequences. Recognizing a poisonous plant, understanding the behavior of animals, knowing when to leave an area before resources were exhausted. These were not abstract lessons, but essential skills. Evening approached gradually. The light softened, shadows lengthened, and the air cooled. Many animals became more active at this time, and early humans had to balance the opportunity to gather food with the increasing presence of predators. Finding a place to rest for the night was an important decision. Elevated ground offered better visibility. Areas near trees provided some protection and the possibility of climbing if necessary. Locations too close to water were avoided because of predators, while completely open ground offered little shelter. Night brought darkness far deeper than most people experience today. Without artificial light, the sky dominated, filled with stars and the pale glow of the Milky Way. Sounds carried farther in the cooler air, the calls of nocturnal animals, the rustle of movement in the brush, the distant roar of predators. Sleep in such conditions was likely light and fragmented. Individuals may have taken turns remaining more alert, though not in a formal or organised way. The presence of others provided some comfort and safety, but the night was never entirely secure. Through all of this, daily life was shaped by rhythm rather than schedules. There were no clocks marking hours, no calendars marking days. Time was measured in hunger and rest, in sunrise and sunset, in the changing of seasons. Seasons themselves influenced behaviour in subtle ways. During wetter periods, food might be more abundant and movement less necessary. During dry periods, longer journeys might be required, and tensions within and between groups could increase as resources became scarce. Despite these challenges, daily life was not only a struggle. There were moments of calm, of quiet observation, of simple presence in the landscape. Sitting in the shade, watching birds move across the water, feeling the wind on the skin, these experiences were part of existence, though they left no trace in the fossil record. There is a tendency to imagine early humans as constantly desperate, but life is rarely lived in a state of unbroken crisis. Even in demanding environments, there are periods of rest, of routine, of small satisfactions, food found and shared. A child learning to crack a nut with a stone. A group moving together across open ground, aware of one another's presence, coordinated in ways that required no words. These quiet moments were the fabric of daily life. Over weeks and months, patterns emerged. Routes between reliable food sources became familiar. Sheltered resting places were remembered. Knowledge accumulated, not in written form, but in memory and habit. And yet, every day still held uncertainty. Weather could change, predators could appear, food sources could fail. Flexibility was essential, and those who adapted more effectively were more likely to survive and pass on their traits. Homo Rudolfensis lived in this balance between routine and unpredictability, between cooperation and competition, between the immediate needs of survival and the gradual shaping of behaviours that would, over countless generations, contribute to the emergence of later human species. When we think about their daily lives, it is easy to focus on movement and food, but diet itself is a story worth exploring more closely. What exactly did they eat, and how did their environment shape those choices? Food was not a matter of preference for Homo Rudolfensis. It was a constant, practical concern, something that shaped every decision about where to travel, when to rest, and how long to remain in one place. Hunger was not an occasional inconvenience as it often is in the modern world. It was a steady presence, a quiet signal from the body that guided daily life. To understand what they ate, it helps to picture the range of foods available in East Africa during that period. The landscape offered variety but not always abundance, and the availability of different foods changed with the seasons. A group might find certain fruits plentiful for a few weeks, only to see them disappear as trees finished bearing. Grasses produce seeds at specific times of year. Tubers could be dug from the ground, but finding them required knowledge of where to look and how to recognize the plants above the surface. Plant foods likely formed a substantial part of the diet. Fruits were valuable when available, providing sugars and moisture. Wild figs, berries, and other seasonal fruits grew in wooded areas near water. These foods were relatively easy to gather and required little processing, but they were not always predictable. Leaves and stems were another resource, though tougher and less energy-rich. Some plants could be chewed directly, while others required more effort to break down. The structure of the teeth in Homo Rudolfensis suggests they were capable of processing relatively coarse plant material, and the broad face and strong jaw muscles may have supported this kind of chewing. Roots and tubers were particularly important, because they were often available even when other foods were scarce. Digging them out required effort and sometimes tools, but they provided carbohydrates and could be found in many environments. Early humans likely used sticks or stones to loosen soil, a simple but effective method. Seeds and nuts added another layer to the diet. These foods were energy-dense but sometimes difficult to access. Hard shells required cracking, and this is where simple stone tools or heavy rocks could be useful. Watching modern primates use stones to break open nuts offers a glimpse of how such behaviour might have looked. Insects were also an important source of nutrition, though they are easy to overlook from a modern perspective. Termites, ants, beetle larvae and other insects were abundant in many parts of the African landscape. They provided protein and fat, and they could be collected in significant quantities with patience. Breaking open termite mounds or turning over decaying wood could yield hundreds of insects in a short time. Honey may have been another prized resource, though more difficult to obtain. Bees' nests in hollow trees or underground cavities offered rich, energy-dense food, but reaching them required persistence and sometimes risk. While plant foods and insects were reliable components of the diet, meat also played a role, though probably not in the regular large quantities seen in later human societies. Hunting large animals would have been difficult for early humans without advanced tools or coordinated strategies. However, scavenging provided opportunities. Predators often left behind partially eaten carcasses, and early humans could take advantage of these remains if they arrived after the predators had moved on. Using sharp stones, they could cut away strips of meat or break bones to extract marrow, a rich source of calories. This behaviour required awareness and timing. Approaching a carcass too soon could be dangerous, but waiting too long meant losing the opportunity to other scavengers. The ability to read signs in the environment, tracks, smells, the presence or absence of certain birds would have been invaluable. Fish and other aquatic resources may also have been part of the diet in areas near lakes and rivers. Shallow waters sometimes trapped small fish, and shellfish or crustaceans could be collected along shorelines. These foods required less pursuit than large animals and provided useful nutrients. One of the most important aspects of early human diet was flexibility. Unlike many animals that rely heavily on a narrow range of foods, early members of the genus Homo appear to have been generalists. They could eat a wide variety of foods depending on what was available. This adaptability was a powerful advantage in environments that changed over time. Flexibility in diet is also linked to changes in anatomy. The teeth of Homo Rudolfensis were different from those of earlier hominins in ways that suggest a varied diet. While still relatively large compared to modern humans, they show patterns of wear that indicate the consumption of both tough plant material and softer foods. Chemical analysis of fossil teeth using isotopes preserved in the enamel provides additional clues. These analyses can reveal the types of plants that form the base of the food chain, whether diets relied more on grasses, fruits, or other vegetation. Such studies suggest that early humans often consumed a mix of foods from different environments. Sharing food within groups may also have been an important behaviour. Large food items, such as scavenged meat, could be difficult for a single individual to consume before spoilage or competition intervened. Sharing increased the chances that valuable resources were used efficiently and may have strengthened social bonds. Social eating, even in its simplest form, is significant. Gathering around food creates opportunities for communication, observation, and learning. Young individuals watching adults process food or use tools would have absorbed skills that improved their own chances of survival. Cooking, which would later transform human diets, by making food easier to digest and increasing caloric intake, was probably not yet part of daily life for Homo Rudolfensis. Without controlled fire, most foods were eaten raw. This required strong teeth and jaws and limited the types of foods that could be consumed efficiently. The absence of cooking also meant that digestion required more energy and time. Raw plant materials are often fibrous and difficult to break down, and raw meat is tougher than cooked meat. These constraints influenced how much food could be eaten and how much energy could be extracted from it. Seasonal variation added another layer of complexity. During wet seasons, fruits and vegetation might be abundant and insects plentiful. During dry seasons, reliance on roots, tubers, and occasional scavenging may have increased. Movement patterns likely shifted in response, with groups travelling to areas where food was more reliable. Knowledge of the landscape played a critical role in these decisions. Remembering where certain plants grew, where animals gathered, where water persisted longest during droughts, these were forms of intelligence just as important as tool use. There is also evidence that early humans selected specific stones suitable for tool making, sometimes transporting them over distances. This suggests planning, the anticipation of future needs. Food processing, whether cutting meat or cracking nuts, required tools, and tools required appropriate raw materials. The connection between diet and brain evolution is often discussed. Larger brains require more energy, and access to higher calorie foods, including meat and marrow, may have supported gradual increases in brain size. While Homo Rudolfensis did not yet have brains as large as later humans, their dietary flexibility may have been part of this broader evolutionary trend. It is interesting to reflect on how much of daily thought must have been devoted to food, where to find it, how to obtain it, how to avoid danger while gathering it. Modern life often separates us from these concerns, but for most of human history, securing food was the central task around which everything else revolved. Yet even in this constant search, there would have been moments of satisfaction, a successful find of ripe fruit, the discovery of a termite mound rich with insects, the chance to scavenge from a carcass before other animals arrived. These small successes sustained both body and group. Children would have learned gradually, first by watching, then by imitating. Identifying edible plants, recognizing the signs of animals, understanding how to use simple tools, these were skills built over years of observation and practice, and while much of the diet consisted of gathering and opportunistic scavenging, the ability to use tools, even in their simplest form, marked an important shift in how early humans interacted with their environment. Tools extended the reach of hands and teeth, allowing access to foods that would otherwise have been difficult or impossible to obtain. Long before machines, metal, or even fire became reliable companions of human life, there were hands and stones. The partnership between the two began so quietly that, if you had been standing in the landscape of East Africa nearly 2 million years ago, you might not have noticed anything unusual at all. A figure crouches, picks up a rock, strikes it once, twice, and then uses the newly sharpened edge to cut or scrape. No sparks, no noise beyond the small click of stone on stone, and yet in that simple act something important was happening. A being was deliberately reshaping part of the environment to serve a purpose. The hands of early humans, including Homo Rudolfensis, were already different from those of most other primates in subtle but significant ways. The thumb was strong and capable of pressing firmly against the fingers, allowing for a precision grip. This grip made it possible to hold small objects securely, to manipulate them with care, and to apply controlled force. Precision may sound like a modest advantage, but in evolutionary terms it is powerful. A hand that can hold a sharp flake of stone safely can cut meat more effectively, strip bark, shape wood, or process plant material in ways that teeth alone cannot accomplish. Over time, such advantages accumulate, and behaviours that begin as occasional improvisations become regular practices. Stone tools, in their earliest form, were simple. A suitable stone, often a type that fractured predictably like flint or basalt, was struck with another stone to produce sharp-edged flakes. These flakes could be used immediately without further shaping. The technique required observation and practice, but it did not demand elaborate planning. Archaeologists refer to many of these early tools as part of the Oldowan tradition, named after Olduvai Gorge, where similar tools were first studied extensively. These tools are among the earliest widely recognised evidence of deliberate stone tool production. Whether Homo Rudolfensis itself made such tools, or whether some were produced by closely related species living at the same time, is still discussed among researchers. But the presence of tools in the environments where they lived suggests that early members of the genus Homo were already participating in this quiet technological shift. The word technology may seem too grand for a sharp stone, but in its simplest definition, technology is any tool or method used to solve a problem or accomplish a task. By that definition, these early tools were indeed technologies, small steps in a long progression that would eventually lead to far more complex inventions. What makes these early tools especially interesting is not only that they existed, but that they required intention. Producing a sharp flake is not entirely accidental. It requires selecting the right kind of stone, striking it at an appropriate angle, and recognizing that the resulting edge can be useful. This chain of actions suggests a level of planning, even if only a few steps ahead. Planning in turn depends on memory and anticipation, the ability to imagine a future need and prepare for it. Watching a modern human child learn to use tools provides a gentle analogy. At first, movements are clumsy, objects are dropped. The purpose of tools is not immediately clear, but gradually through observation and repetition, coordination improves, and the connection between action and outcome becomes understood. Early humans likely learned in much the same way, by watching others, imitating successful behaviours, and refining their own movements over time. Tools also extended the kinds of food that could be eaten. A sharp flake could cut through the hide of an animal or slice meat into manageable pieces. A heavy stone could crack bones to release marrow. Sticks could be used to dig for roots or to probe termite mounds. Each of these activities expanded the range of available resources, making early humans more adaptable to changing environments. But tools were not only about food. They may also have been used to shape wooden implements, to strip bark, or to process plant fibres. Wood rarely survives in the fossil record, so we have little direct evidence of such tools from this period, but it is reasonable to think they existed. Stone tools may have been only part of a broader toolkit made from materials that decayed long ago. The act of making tools may also have had a social dimension. Imagine a small group resting in the shade, one individual striking stones together while others watch. A younger member of the group tries the same motion, at first unsuccessfully, then gradually producing a usable flake. Knowledge is shared, not through formal instruction, but through presence and imitation. Such moments, repeated over generations, create traditions, simple at first, but traditions nonetheless. A particular way of striking stone, a preferred type of raw material, a familiar technique passed from one individual to another. In this way, technology becomes part of culture, even before language or symbolic thought becomes fully developed. Hands themselves bear traces of this long partnership with tools. The bones of the hand, the structure of the joints, the arrangement of muscles, all reflect the demands placed on them over millions of years. The ability to grip firmly, to control fine movements, to coordinate both hands together, these traits were shaped not only by anatomy, but by behaviour. Behaviour and anatomy influence each other in a continuous loop. A useful behaviour, such as tool use, creates selective pressure favouring individuals whose anatomy makes that behaviour easier. Over time, those anatomical traits become more common in the population. The brain also plays a role. Coordinating the hand, judging the angle of a strike, recognising the quality of stone, all require sensory processing and motor control. Repeated practice strengthens neural pathways, making actions smoother and more efficient. It is possible that the gradual increase in brain size seen in early Homo species was influenced, in part, by the demands of tool use and other complex behaviours. There is also something quietly symbolic about the first tools. A stone shaped by deliberate action represents a small but meaningful shift in the relationship between organism and environment. Instead of merely adapting to the surroundings, early humans began to alter them, even if only in modest ways. A sharp edge where none existed before, a stick shaped for digging, a bone cracked open to release its marrow. Each of these acts changed the world in small, practical ways. Of course, life was not transformed overnight. These early technologies were simple, and their impact was limited compared to the changes that would come much later. But they mark the beginning of a trend, the gradual accumulation of knowledge and skill that would eventually define humanity. Tools also affected movement and travel. A useful stone might be carried from one place to another, especially if suitable materials were scarce. This suggests an awareness of future needs, the understanding that a tool made today could be useful tomorrow. Such foresight, even in a modest form, represents an important cognitive step. At the same time, tool use required energy and time. Making tools was not effortless. It required attention and practice. Individuals had to balance the effort of producing tools with the immediate demands of finding food and avoiding danger. Daily life remained grounded in practical concerns. Tools were helpful, but they did not eliminate the challenges of the environment. Predators still hunted. Food was still unpredictable. Weather still shaped movement and behaviour. And yet, the presence of tools hints at a subtle change in perspective. The idea that problems could be solved not only through instinct or strength, but through ingenuity. This ingenuity was not dramatic or revolutionary in the way modern inventions often seem. It was quiet, incremental, unfolding over countless small moments. A stone struck here, a stick shaped there, a technique refined through repetition. The pace of change was slow, almost imperceptible within a single lifetime, but across generations it accumulated. It is interesting to imagine what these early humans might have thought, if they thought in ways we could recognize. Did they feel a sense of satisfaction when a tool worked well? Did they notice improvements in their own skill? Or was tool use simply another part of daily life, as ordinary to them as tying shoelaces is to us? We cannot know for certain, but we can see the results in the archaeological record, in the scattered stones bearing marks of deliberate strikes, in the cut marks on fossil bones, in the subtle shifts in anatomy that reflect changing behaviours. Hands, in this sense, were not only instruments of survival, but instruments of change, shaping both the environment and the species itself. Standing upright feels so natural to us that it's easy to forget how unusual it is in the animal kingdom. Most mammals move on 4 limbs. Even our closest living relatives, chimpanzees and gorillas, walk on their knuckles most of the time, rising onto 2 legs only occasionally. Yet for Homo Rudolfensis, walking upright was already an ordinary part of daily life, a behaviour inherited from earlier ancestors, but refined over generations in response to the landscapes of East Africa. To understand why upright walking mattered so much, it helps to imagine the environment again, not just the lakes and wooded patches, but the open ground between them. Distances could be long, food sources were scattered, water might lie kilometres away. Survival often depended on the ability to travel efficiently, conserving energy while covering ground steadily. Walking on 2 legs, though slower than the gallop of a predator or the bounding run of an antelope, is remarkably energy efficient over long distances. The human body, even in its early forms, evolved features that supported this kind of movement. A pelvis shaped to support internal organs while standing, a spine curved to balance the torso, legs longer than arms, and feet structured to push forward with each step. The feet in particular tell a quiet but important part of the story. Earlier hominins already had arches and a forward-aligned big toe, features that improve stability and efficiency when walking. These traits meant that early humans could travel across varied terrain without expending as much energy as an ape moving upright for long periods. For Homo Rudolfensis, this ability would have shaped daily routines. A group might leave a resting place at dawn and walk several kilometres before midday, stopping to gather food, drink or rest in the shade. Later they might continue, adjusting their path in response to what they found. A patch of fruiting trees, the tracks of animals, the distant glint of water. Movement was rarely aimless. It followed patterns learned over time. Routes between reliable food sources became familiar, and individuals likely remembered landmarks, distinctive rock formations, clusters of trees, bends in rivers. Memory turned the landscape into a mental map. Walking upright also offered another advantage, one that is easy to overlook. It freed the hands. Hands that were not needed for locomotion could carry food, tools, or infants. A parent could move while holding a child. An individual could gather fruits or tubers and transport them to others. These small possibilities, repeated day after day, subtly changed the dynamics of survival. There is also the matter of vision. Standing upright raises the head higher above the ground, improving the ability to see over tall grasses or low shrubs. In a world where predators might be hidden from view, even a small increase in visibility could mean the difference between noticing danger early and reacting too late. But walking upright was not effortless, especially for early humans whose anatomy was still evolving. Long distances required endurance, feet and legs tired. Injuries could be serious, and a damaged foot or leg might leave an individual unable to keep pace with the group, a dangerous situation in an environment where isolation increased vulnerability. The ground itself was not always easy to cross. Dry seasons hardened soil into rough surfaces. Wet seasons turned certain areas into mud. Rocky slopes demanded careful footing. River crossings could be treacherous with slippery stones and sudden currents. And then there was the heat. The African sun can be intense, and travelling during the hottest hours of the day risked overheating. Early humans likely timed their movements to cooler parts of the day, resting in shade when the sun was highest. Walking upright may have helped here as well, reducing the amount of body surface directly exposed to the sun compared to moving on all fours, and allowing air to circulate more effectively. Sweating, a trait that later became highly developed in humans, also played a role in cooling the body. Even early members of the genus Homo likely had more efficient thermoregulation than many other mammals, enabling them to remain active for longer periods. Movement across the landscape was not only about reaching destinations, it was also about responding to change. A drying waterhole might force a group to move sooner than expected. A herd of animals passing through an area could signal new opportunities for scavenging. Signs of predators might prompt a detour. Flexibility in movement patterns was essential. Groups that adapted quickly to changing conditions were more likely to survive. Children learned to walk and travel within this demanding context. At first, their steps would have been short and unsteady, and they would have depended on adults for protection and guidance. Over time, they gained strength and coordination, learning to keep pace, to watch the ground for hazards, to recognize the signs that guided movement. Travel was not silent. Feet brushed against grasses, stones shifted underfoot. Voices, though simple, may have been used to keep contact within the group. Occasional laughter or play among younger members likely occurred during safer moments, reminders that even in a challenging world, life contained elements of curiosity and social connection. Night travel was probably rare and avoided when possible. Darkness limited visibility and increased the risk of encountering predators. Groups would have sought resting places before nightfall, selecting locations that offered some protection and a clear view of the surroundings. The ability to move efficiently also influenced how early humans interacted with other species. Some animals migrated seasonally, and following these movements could lead to new food sources. Others avoided certain areas, signalling environmental changes that humans could also detect. Walking upright allowed early humans to explore a wider range of habitats, from lakeshores to grasslands to wooded areas, without being confined to a single ecological niche. This flexibility became one of the defining characteristics of the genus Homo. Over generations, the anatomy of early humans continued to adapt to this lifestyle. Bones became more robust in areas that bore weight. Joints evolved to handle the stresses of the long-distance walking. Muscles developed patterns of use that improved endurance. These changes did not occur suddenly. They accumulated gradually, shaped by countless journeys taken by individuals whose names and stories are lost to time. It is interesting to reflect on how movement shapes perception. Walking through a landscape at a steady pace allows the mind to observe, to notice patterns, to remember routes and resources. The rhythm of steps, the shifting light, the changing sounds, all contribute to a form of awareness that is different from the hurried movement of modern life. For Homo Rudolfensis, walking was not exercise or recreation. It was simply part of being alive. Each step connected them to water, to food, to shelter, to one another. Looking at a fossil skull, it is tempting to think of the brain simply as a number, a measurement expressed in cubic centimetres, a comparison between one species and another. Scientists do measure these things carefully, and those numbers do matter. But a brain is not only its size, it is also its structure, its organisation, and the demands placed upon it by daily life. When we consider Homo Rudolfensis, the phrase, "the brain that was growing," does not mean a sudden leap or transformation. It means a gradual shift, a slow accumulation of changes shaped by the challenges of living in a complex and changing world. To begin with, brain size in early humans was already larger than in most earlier hominins. Australopithecines, who lived before members of the genus Homo became widespread, typically had brain volumes around 400 to 500 cubic centimetres, not much larger than those of modern chimpanzees. Fossils attributed to Homo Rudolfensis suggest cranial capacities that could reach roughly 700 cubic centimetres or more, depending on the specimen and interpretation. That increase may not sound dramatic compared to the modern human average of around 1,300 to 1,400 cubic centimetres, but in evolutionary terms it represents a significant step. An increase in brain size does not happen without cost. The brain is an energy-hungry organ. Even in modern humans, it consumes a substantial portion of the body's daily energy, far more than most other organs relative to its weight. For early humans, whose access to food was unpredictable, any increase in brain size required dietary and behavioural changes that made such an energy investment worthwhile. This connection between diet and brain development is often discussed, and for good reason. Access to higher calorie foods, including animal fats and marrow when available, may have provided the energy necessary to support larger brains. But energy alone is not the whole story. A larger brain is useful only if it provides advantages in survival and reproduction. What kinds of advantages might a growing brain have offered Homo Rudolfensis? One possibility lies in memory. Living in a landscape where resources were scattered and seasonal, the ability to remember locations of food, water, and shelter would have been valuable. Recognizing patterns in the environment, knowing when certain fruits ripened or where animals tended to gather, could reduce the time and energy spent searching. Memory also supports social life. Recognizing individuals, remembering alliances or conflicts, and understanding the behavior of others are complex tasks. Even in modern primates, social interactions require significant cognitive processing. Early humans likely lived in small groups where cooperation and awareness of group members were essential. Another advantage may have been improved problem solving. The use of tools, even simple ones, requires planning and coordination. Selecting the right stone, striking it correctly, and using the resulting edge effectively involve multiple steps. Repeating these steps successfully suggests the presence of learning and refinement over time. Learning itself is closely tied to brain development. The ability to observe others and imitate useful behaviors allows knowledge to spread within a group without requiring each individual to discover everything independently. This form of social learning is one of the foundations of culture, even in its simplest forms. Communication also places demands on the brain. While Homo Rudolfensis almost certainly did not possess language in the complex form used by modern humans, they likely used a range of vocalizations, gestures, and facial expressions. Interpreting these signals and responding appropriately requires neural processing and coordination. It is important to remember that brain evolution is not only about intelligence in the abstract sense, it is about adapting to specific environments and ways of life. A brain suited to navigating dense forests may differ in structure and emphasis from one adapted to open savannas. The growing brains of early humans were shaped by the particular challenges of their surroundings, finding food in varied habitats, avoiding predators, maintaining social bonds, and learning from experience. When scientists study fossil skulls, they sometimes create endocasts, models of the interior of the skull that approximate the shape of the brain. These endocasts do not preserve fine details of brain structure, but they can reveal general features, the size of different regions, the position of grooves and ridges that correspond to folds in the brain's surface. In some early Homo fossils, including those attributed to Homo Rudolfensis, there are hints of changes in areas associated with higher cognitive processing. These changes are subtle and open to interpretation, but they suggest that brain organization, not just size, was evolving. Another aspect of brain growth is the extension of childhood. In many species, including humans, larger brains are associated with longer developmental periods. A longer childhood allows more time for learning, for acquiring the skills needed to survive in complex environments. It also requires greater parental investment and social support. While we cannot know the exact length of childhood in Homo Rudolfensis, comparisons with other early humans suggest that developmental periods were gradually increasing. This would have strengthened social bonds within groups, as adults spent more time caring for and teaching young individuals. Teaching, even in simple forms, represents an important step in cognitive evolution, demonstrating how to crack a nut, where to find edible plants, or how to recognize danger involves awareness of another individual's needs and abilities. It reflects a level of social understanding that goes beyond instinct. There is also the question of awareness itself. What did it feel like to be Homo Rudolfensis? This is something we cannot answer directly, but we can consider what awareness means in a biological sense. Awareness arises from the brain's ability to process sensory information, to form memories, to anticipate outcomes, and to guide behavior. Even without complex language or abstract reasoning, early humans would have experienced the world vividly. The heat of the sun, the taste of food, the sound of wind in grass, the sight of approaching animals, these sensations were immediate and meaningful. The brain, even at this stage of development, was capable of integrating these experiences into a coherent perception of the world. Emotions too likely played a role. Fear in the presence of predators, satisfaction after finding food, attachment to offspring or companions, these responses are deeply rooted in mammalian biology and would have been present in early humans. The growing brain was not only a tool for survival, but also the centre of experience itself. Another factor to consider is variability. Brain size and shape can vary within a species, just as height or other physical traits do. Not every individual of Homo Rudolfensis would have had exactly the same brain capacity or structure. Evolution works on populations, not individuals, and variation provides the raw material for natural selection. Over many generations, small differences that provided advantages could become more common. This gradual process, repeated across thousands of years, produced the larger and more complex brains seen in later human species. The environment continued to play a crucial role in shaping these changes. Climate fluctuations, shifting habitats, and interactions with other hominin species created pressures that favoured adaptability. A brain capable of flexible behaviour, of adjusting strategies in response to changing conditions was a valuable asset. Flexibility may be one of the most important traits in human evolution. Specialists thrive in stable environments, but generalists, organisms capable of using a wide range of resources and behaviours, are better suited to environments that change. Early humans, including Homo Rudolfensis, appear to have been generalists, and their growing brains supported that versatility. There is also an interesting feedback loop between brain growth and social complexity. Larger brains enable more complex social interactions, and complex social groups create new cognitive demands, remembering relationships, interpreting signals, coordinating actions. This cycle may have contributed to the steady expansion of cognitive abilities in the human lineage. At the same time, brain growth did not occur in isolation from the rest of the body. Changes in diet, locomotion, and tool use all interacted with cognitive evolution. The story of the growing brain is inseparable from the broader story of how early humans lived. It is worth reflecting for a moment on how gradual these changes were. From the perspective of a single lifetime, there would have been little noticeable difference between generations. A child growing up in a group of Homo Rudolfensis would have lived much as their parents did, facing similar challenges and learning similar skills. Only when viewed across vast stretches of time does the pattern become clear. A slow, steady trend toward larger and more complex brains, accompanied by changes in behaviour and culture. This gradual pace is easy to overlook in a world accustomed to rapid change, but it is the rhythm of evolution. Small variations, tiny advantages, repeated over thousands of generations, shaping the trajectory of a lineage. By the time Homo Rudolfensis was moving across the landscapes of East Africa, the human story was already far from simple. There was no single kind of early human walking the land, no solitary lineage quietly marching toward the present. Instead, several closely related species shared the same broad region, sometimes separated by rivers or distance, sometimes living close enough that they might have seen one another from afar. It is a strange thought at first, because we are so accustomed to thinking of humanity as one species. Today, every person alive belongs to Homo sapiens. Differences exist, of course, in language, culture, and appearance, but biologically we are remarkably similar. 2 million years ago, that was not the case. The world contained multiple kinds of humans, each adapted in slightly different ways, each following its own evolutionary path. Among these neighbours were individuals often classified as Homo habilis, a species known from fossils found in East and South Africa. Homo habilis had smaller brains on average than those attributed to Homo Rudolfensis, and the structure of the face and teeth differed in subtle ways. Some scientists have argued that the two species may represent variations within a single population, while others maintain that the anatomical differences are consistent enough to justify separate names. The debate itself reflects how difficult it can be to draw clear boundaries in the fossil record. Regardless of classification, it is likely that individuals resembling what we call Homo habilis and Homo Rudolfensis lived in overlapping regions. They may have used similar tools, eaten similar foods, and travelled across the same landscapes. Yet small differences in body size, diet, or behaviour could have allowed them to occupy slightly different ecological niches, reducing direct competition. Another presence in this ancient world was Australopithecus boisei, a hominin with a very different appearance. Australopithecus boisei had a massive jaw, large teeth, and a skull adapted for powerful chewing. These features suggest a diet focused on tough fibrous plant material, perhaps including roots, tubers, and grasses that required significant processing. If Homo Rudolfensis was a generalist, capable of eating a wide range of foods, Australopithecus boisei may have been more specialised. Specialisation can be effective in stable environments, allowing a species to exploit resources that others cannot easily use. But specialisation also carries risks. When conditions change, specialists may struggle to adapt. The coexistence of these different hominins meant that early humans were not only responding to the challenges of climate and predators, but also to one another. Competition for food, water and territory may have influenced behaviour, even if direct conflict was rare. It is worth imagining what an encounter between two different early human species might have been like. At a distance, they would have recognised one another as similar but not identical. Body shapes, facial features, and patterns of movement would have differed slightly. Vocalizations may have sounded unfamiliar. There might have been caution, curiosity, perhaps even avoidance. In many animals, closely related species share territories without frequent aggression, as long as resources are sufficient and each species occupies its own niche. It is possible that early humans behaved in similar ways, keeping distance when necessary and focusing on their own activities. Still, there would have been times when paths crossed at water sources or feeding grounds. Lakes and rivers drew animals of all kinds, and early humans were no exception. At such places, awareness and caution would have been essential, not only because of predators, but because of other hominins who might compete for the same resources. Competition does not always mean violence. Often it takes the form of subtle adjustments, one group arriving earlier at a feeding site, another moving to a different area, patterns of movement shifting over time. These small changes can shape the distribution of species across landscapes without dramatic confrontations. There is also the possibility, though difficult to prove, that some early human species occasionally interbred. Genetic evidence from much later periods shows that Homo sapiens interbred with Neanderthals and Denisovans, leaving traces of those encounters in modern DNA. Whether similar exchanges occurred among earlier species like Homo Rudolfensis and their contemporaries is uncertain, but it cannot be ruled out entirely. The fossil record preserves bones, not behaviour, and so much of what happened between these groups remains beyond our reach. Yet the presence of multiple species in the same regions tells us that early human evolution was not a solitary journey, but a shared experience, a mosaic of lineages adapting to similar challenges in different ways. Another neighbour that appeared somewhat later, but whose roots may overlap with the time of Homo Rudolfensis, was Homo erectus. This species would become one of the most successful early humans, spreading beyond Africa into parts of Asia and Europe. Homo erectus had a larger brain on average, a more elongated body adapted for long-distance walking, and a greater reliance on tools. The emergence of Homo erectus marks an important transition in human evolution, but it did not happen overnight. Early populations of Homo erectus likely coexisted with other hominins for extended periods. The boundaries between species were not sharp lines but gradual transitions. Living in a world with multiple human species also raises questions about perception and identity. Did individuals of Homo Rudolfensis recognize others as different in a meaningful way? Did they distinguish between their own group and others, not only socially but biologically? These are questions we cannot answer directly, yet it is reasonable to think that visual and behavioural differences were noticed, just as modern humans notice differences among other animals. Predators, of course, did not distinguish between species in the same way. To a large carnivore, any hominin represented potential prey or competition. This shared vulnerability may have shaped behaviour in subtle ways, encouraging vigilance and group cohesion. Sharing the landscape with other hominins also meant sharing knowledge indirectly. The presence of stone tools at certain sites might have signalled useful resources nearby. Tracks or remains left by one group could inform another about the movements of animals or the location of water. In this sense, the activities of different species were interconnected, even if they did not interact directly. It is also possible that different species developed slightly different strategies for survival. One group might have relied more heavily on plant foods, another on scavenging. One might have preferred certain habitats, another different ones. These variations reduced direct competition and allowed multiple species to persist in the same region for long periods. But coexistence does not last forever. Over time, environmental changes, shifts in climate, and the gradual evolution of new species altered the balance. Some lineages became more adaptable, others more vulnerable. Extinction, as always, was a possibility. When we look back across millions of years, it is easy to see the eventual outcome: Homo sapiens as the sole surviving human species. But from the perspective of the past, that outcome was far from certain. For most of human evolutionary history, diversity was the norm. The disappearance of Homo Rudolfensis and other early hominins was not a sudden event, but a gradual process. Populations shrinking, ranges contracting, until eventually no individuals remained. The reasons are complex and likely varied from place to place, involving climate shifts, competition, and chance. Yet their existence left a lasting legacy. Each species contributed to the broader pattern of human evolution, exploring different adaptations, shaping environments, and passing on traits that would influence later lineages. There is something quietly humbling in recognizing that our own species is part of this larger tapestry, not the inevitable endpoint of evolution, but one branch among many, fortunate enough to persist. And when we consider the neighbours of Homo Rudolfensis, their rivals and companions in that ancient landscape, we begin to see the human story not as a straight path, but as a crowded and dynamic world, full of interactions, experiments and possibilities. From this perspective, another question naturally emerges. If multiple species lived side by side, sharing resources and adapting to changing conditions, what determined which lineages survived and which disappeared? No species, however well adapted, last forever. When we look at the fossil record, extinction is not the exception but the rule. Entire lineages appear, persist for thousands or even millions of years, and then gradually fade from the world, sometimes leaving descendants, sometimes leaving nothing but fragments of bone and a name. Homo Rudolfensis belongs to this long list of vanished species, and like many of them, its disappearance was probably not a single dramatic event, but a slow, complex process shaped by many small changes over time. One of the most important influences on the fate of early humans was climate. East Africa, where Homo Rudolfensis lived, experienced repeated cycles of environmental change. Periods of wetter climate allowed forests and woodlands to expand, while drier periods favoured open grasslands. Lakes grew and shrank, rivers changed course, vegetation shifted, and with it, the animals that depended on that vegetation. For a species to survive such changes, flexibility was essential. Diet, movement patterns, and social behaviour all had to adjust to new conditions. Some species were well suited to this kind of variability. Others were more specialised and therefore more vulnerable when their preferred habitats declined. Homo Rudolfensis appears to have been somewhat flexible in diet, but flexibility alone does not guarantee survival. Other hominin species were also adapting, and some of them may have done so more effectively under certain conditions. Competition is another factor that may have played a role. The period in which Homo Rudolfensis lived was one of increasing diversity within the genus Homo. Populations that would later be classified as Homo erectus were emerging, showing anatomical features associated with greater endurance, more efficient walking, and perhaps more advanced tool use. If Homo erectus populations were better able to travel long distances, exploit varied resources, and adapt to changing climates, they may have gradually expanded into territories once occupied by other hominins. This would not necessarily have involved direct conflict. More often, competition in nature takes the form of one species slowly outcompeting another for food or habitat, reducing the latter's population over generations. Population size itself is an important factor. Small populations are more vulnerable to extinction because they are less able to recover from losses caused by disease, drought, or other challenges. A few difficult years can have lasting effects if there are not enough individuals to sustain the group. Fossil evidence suggests that Homo Rudolfensis was never widespread or abundant compared to some later species. If their populations were relatively small and localized, they would have been particularly sensitive to environmental changes. There is also the question of reproduction and growth rates. Species with slower reproduction may struggle to recover after population declines. While we cannot know the exact reproductive patterns of Homo rudolfensis, comparisons with other early humans suggest that raising young required significant time and care. This would have limited how quickly populations could expand. Disease may have played a role as well, though this is difficult to detect in the fossil record. Pathogens leave few traces on bones, and outbreaks in small populations could have reduced numbers without leaving clear evidence for scientists to find millions of years later. Predation remained a constant risk. Early humans were not at the top of the food chain. Large carnivores, including big cats and hyena-like scavengers, would have preyed on vulnerable individuals, especially children or those injured or isolated. While predation alone is unlikely to cause extinction, it contributes to the pressures that shape population dynamics. Another factor to consider is the pace of evolutionary change itself. Evolution does not move at a constant rate. Sometimes new traits spread rapidly through a population, at other times change is slow. If other hominin species developed advantageous traits more quickly, whether in tool use, social organisation, or mobility, they may have gradually replaced less adaptable populations. It is important to remember that extinction is often a quiet process. There is no single moment when the last individual of a species is recognised as such. Instead, numbers decline. Groups become smaller and more isolated. Fewer young survive to adulthood. Over generations, the species becomes rarer until eventually none remain. From the perspective of those living at the time, this process would have been invisible. Each generation would have known only its own struggles and successes, unaware that they were part of a lineage nearing its end. The disappearance of Homo rudolfensis may also reflect broader patterns in human evolution. Early Homo species often overlapped in time and space, but only some lineages persisted long enough to give rise to later forms. Others, equally successful for long periods, eventually reached dead ends in evolutionary terms. This does not mean they were inferior or poorly adapted. Homo rudolfensis survived for hundreds of thousands of years, a span far longer than the entire history of modern civilization. By any reasonable measure, that represents a successful species. Extinction, in many cases, is not a failure, but a natural outcome of changing conditions. Environments change, competitors arise, and the balance of advantages shifts. A species well suited to one set of conditions may find itself less suited to another. It is also possible that Homo rudolfensis did not disappear entirely in isolation, but contributed genetically to other populations. If interbreeding occurred with related species, some traits may have been absorbed into emerging lineages, leaving no clear boundary between extinction and transformation. The fossil record rarely preserves enough detail to confirm such events for very early periods, but the possibility remains. The fading of Homo rudolfensis was part of a broader reshaping of the human landscape. As time passed, species like Homo erectus became more widespread, eventually spreading beyond Africa into other continents. Tool technologies became more refined, patterns of movement changed. The human story continued, but the specific branch represented by Homo rudolfensis gradually disappeared. There is something quietly poignant in this realization. A species that lived, moved, learned, and survived for hundreds of thousands of years eventually vanished, leaving behind only a few fossils and the questions they inspire. Yet their disappearance also reminds us of the resilience and adaptability required for survival over long spans of time. The traits that allowed some human lineages to persist, flexibility, cooperation, learning, were shaped in part by the pressures faced by earlier species like Homo rudolfensis. In that sense, their legacy did not end with their extinction. It continued in the broader patterns of human evolution, in the traits passed down through generations, in the ways early humans learned to navigate a changing world. The story of Homo rudolfensis, like the story of nearly every ancient species, rests on fragments, not complete skeletons laid out in perfect order, Not preserved scenes of daily life, but scattered pieces of bone, sometimes worn, sometimes broken, sometimes found many kilometers apart. From these fragments, scientists attempt to reconstruct not only the bodies of individuals, but entire populations, environments, and timelines. It is a process that requires patience, caution, and a willingness to accept uncertainty. To begin with, fossils themselves are rare. When an animal dies, its body usually disappears quickly. Scavengers carry away bones, weather breaks them down, bacteria and insects consume soft tissues, and within a relatively short time, little remains. For a fossil to form, a precise sequence of events must occur. The remains must be buried relatively quickly, often by sediment carried by water or wind. Oxygen levels must be low enough to slow decay. Minerals gradually replace the organic material, turning bone into stone while preserving its structure. Even under favourable conditions, only a small fraction of living organisms become fossils, and only a small fraction of those fossils are ever discovered. This means that the fossil record is not a complete archive, but a patchwork, a collection of surviving traces that hint at a much larger and more complex past. When scientists search for fossils, they often walk slowly across exposed ground, scanning for shapes and textures that stand out from the surrounding rock. A fragment of jaw may appear as a slight curve in the sediment. A tooth may catch the light differently than a stone. These discoveries often begin with something very small, a single piece that suggests more may lie beneath the surface. Excavation is careful work. The surrounding sediment is removed gradually, sometimes grain by grain, to avoid damaging fragile bones. Each fragment is documented, photographed, and mapped in its original position. The orientation of a fossil, the layer of sediment in which it is found, and its relationship to other remains all provide clues about age and environment. Once removed from the ground, fossils are often encased in protective jackets of plaster or other materials for transport. In laboratories, technicians and researchers clean the specimens with fine tools, sometimes working for weeks or months to remove hardened sediment without harming the fossil itself. Reconstruction is another delicate process. Fossils are rarely complete. Pieces must be aligned and joined, sometimes with small gaps where bone is missing. In some cases, casts of mirror image bones or comparisons with related species help fill in the missing parts. Every step requires judgment, and every reconstruction carries a degree of interpretation. This is one of the reasons scientific debates arise. When different researchers examine the same fossils, they may interpret certain features differently. A slight difference in how fragments are aligned can change measurements. A small variation in the curvature of a bone may be seen by one scientist as evidence of a separate species, while another may view it as normal variation within a population. The skull known as KNM-ER 1470, associated with Homo Rudolfensis, provides a well-known example. Early reconstructions suggested a relatively flat face and large brain case, features that distinguished it from other early Homo fossils. Later studies revisited the reconstruction, questioning whether some parts had been positioned in ways that exaggerated those differences. These debates are not signs of failure or confusion in science. They are part of the process of refining knowledge. New techniques, new discoveries, and new perspectives all contribute to a more accurate understanding over time. Dating fossils is another area that requires careful work. Scientists cannot simply look at a bone and know its age. Instead, they rely on the layers of rock in which fossils are found and on various methods of radiometric dating. Volcanic ash layers, common in regions like East Africa, are particularly valuable because they often contain minerals that can be dated with precision. By measuring the decay of certain isotopes, researchers can estimate how long it has been since the ash was deposited. Fossils found between such layers can then be assigned approximate ages. These methods do not produce exact dates in the way a calendar does, but they provide reliable ranges that help place species within a timeline. Another important tool is comparative anatomy. Scientists compare fossils from different sites and time periods, looking for patterns in bone structure, tooth shape, and cranial features. These comparisons help identify relationships among species and track changes over time. Teeth in particular are valuable sources of information. Enamel is extremely durable, and teeth often survive when other bones do not. The size, shape, and wear patterns of teeth can reveal details about diet, age, and even aspects of behavior. Microscopic analysis of tooth wear can indicate whether an individual consumed tough plant material, softer fruits, or foods that contained grit or sand. Chemical analysis can reveal the types of plants at the base of the food chain, providing clues about the environment in which the individual lived. Despite these tools, the fossil record remains incomplete, and gaps in evidence often lead to differing interpretations. One group of researchers may argue that certain fossils represent a distinct species, while another group may see them as variations within the known species. These discussions sometimes continue for decades, with new discoveries shifting the balance of evidence. A single additional fossil can support one interpretation or challenge another. Scientific debates are shaped not only by evidence, but also by the broader frameworks researchers use to interpret that evidence. Some scientists prefer to recognize more species, emphasizing anatomical differences and diversity. Others prefer to group fossils into fewer species, emphasizing variation within populations. Both approaches have merit, and the balance between them changes as new data become available. The debates surrounding Homo Rudolfensis reflect this broader pattern. Some researchers consider it a distinct species, pointing to differences in skull shape, facial structure, and dental proportions. Others argue that these differences fall within the range of variation expected for Homo habilis or other early Homo populations. These discussions may seem technical, but they matter because they shape how we understand human evolution. Recognizing multiple species living at the same time suggests a more complex and branching evolutionary history. Grouping fossils into fewer species suggests a more gradual and continuous process of change. Another challenge in interpreting fossils is the limited number of specimens. A modern biologist studying a living species can examine hundreds or thousands of individuals, observing variation across age, sex, and geography. Paleoanthropologists often work with only a handful of fossils, sometimes only a single skull or jaw to represent an entire population. This makes it difficult to distinguish between normal variation and true species-level differences. A large skull might represent a male in a species where males are larger than females. A robust jaw might reflect dietary differences rather than genetic ones. Without large sample sizes, conclusions must remain tentative. Technology has gradually improved the tools available to researchers. CT scanning allows scientists to examine the internal structure of fossils without damaging them. Digital modelling makes it possible to reconstruct missing parts or compare shapes with great precision. Three-dimensional scans can be shared among researchers around the world, allowing for broader collaboration and analysis. These advances have not eliminated debates, but they have provided new ways to test hypotheses and refine interpretations. There is also an important human element in scientific work. Fossil discoveries are often made in challenging environments, requiring teams of researchers, local guides, technicians, and students working together. Field seasons can be physically demanding, with long days under intense heat, careful documentation, and the constant hope of finding something significant. The moment of discovery, when a fossil first emerges from the sediment, is often quiet rather than dramatic. A fragment appears, and slowly, carefully it is revealed. The excitement builds gradually as the significance becomes clear. Back in laboratories and museums, the work continues in a different rhythm, measuring, comparing, discussing, writing, revising. Scientific papers present conclusions, but behind those conclusions lie years of effort and collaboration. Museums play a role as well. Fossils are preserved, catalogued and displayed, allowing both scientists and the public to see the evidence firsthand. Casts of important specimens travel to institutions around the world, helping students and researchers learn about human evolution. Public interest in fossils has grown over time, and discoveries often capture the imagination. There is something compelling about holding a piece of bone that belonged to a being who lived nearly 2 million years ago. It creates a sense of connection across time, a reminder that humanity's story is far older and more complex than our written histories. Yet fossils are only part of the evidence. Archaeological sites, stone tools, animal remains, and environmental data all contribute to the reconstruction of ancient lives. Each piece adds context, helping scientists understand not only what early humans looked like, but how they lived. Even with all this information, uncertainty remains. Science does not provide absolute certainty about the distant past. It provides the best explanations supported by available evidence, explanations that are always open to revision as new discoveries are made. This openness is one of the strengths of scientific inquiry. Ideas are tested, challenged, and refined. Debates continue, sometimes for generations, gradually bringing us closer to understanding. The story of Homo Rudolfensis, shaped by fossils and fragments, and the discussions that surround them, is still evolving. New discoveries in East Africa and elsewhere may clarify relationships among early human species or reveal entirely new branches of the human family tree. When a fossil skull is lifted from the earth, what scientists see at first is not a face in the familiar sense. There is no skin, no expression, no eyes, no colour, no voice. Only bone remains, silent and mineralised, shaped by muscles that vanished millions of years ago. And yet, from that bone, researchers attempt something remarkable. They try to reconstruct a face, not perfectly, not with complete certainty, but with enough accuracy to give us a glimpse of an individual who once lived, breathed, and moved through a real landscape. This process is part science, part careful inference, and part restrained imagination. It begins with the skull itself, because the skull holds a surprising amount of information. The structure of the face, the position of the eye sockets, the shape of the jaw, and the contours of the cheekbones all provide clues about how the soft tissues once lay over the bone. Scientists begin by studying the skull in detail, often using high-resolution scans to capture its exact shape. CT scanning allows researchers to see not only the outer surface, but also the internal structure, revealing thickness, density, and areas that may have been distorted over time. Fossils are rarely perfect. They may be compressed by sediment, cracked, or missing sections entirely. Digital reconstruction allows scientists to correct some of these distortions, carefully adjusting the shape to approximate the original form. Once the skull has been reconstructed as accurately as possible, the next step is to understand how muscles attach to bone. Muscles leave subtle marks, small ridges or roughened areas where tendons once anchored. These markers indicate the size and placement of muscles that control chewing, facial movement, and jaw strength. In species like Homo Rudolfensis, the muscles used for chewing were likely powerful, especially compared to modern humans. The broad face and strong jaw suggest that the muscles of the cheeks and temples were well developed, capable of generating significant force. These anatomical clues guide scientists in estimating how thick certain muscle layers may have been. Another important factor is the relationship between bone and soft tissue thickness. In modern forensic science, researchers have measured average tissue depths at specific points on the skull in living populations. While these measurements cannot be applied directly to extinct species, they provide a starting point. Comparisons with modern humans and other primates help establish reasonable estimates for early hominins. Using these estimates, scientists place markers on a replica of the skull, indicating the approximate thickness of skin and tissue at various locations. These markers act like a framework, guiding the gradual building of a face. The reconstruction itself may be done in clay, digital modelling software, or a combination of both. Layer by layer, muscles are added, following the anatomical structure known from modern primates and humans. The position of the nose is estimated from the shape of the nasal opening and surrounding bone. The lips are inferred from the structure of the teeth and jaws. The eyes are placed within the sockets at anatomically consistent positions. At each step, the reconstruction is guided by evidence rather than guesswork, but there is always a margin of uncertainty. Skin texture, hair distribution, coloration, and expression cannot be known with precision. These aspects are informed by comparisons with related species and by reasonable assumptions about adaptation to climate and environment. For example, early humans living in equatorial Africa likely had skin adapted to intense sunlight, which suggests darker pigmentation, though the exact shade cannot be determined. Hair patterns are even more uncertain. Body hair in early Homo species was probably reduced compared to apes, but more extensive than in modern humans, yet the precise appearance remains unknown. Because of these uncertainties, responsible reconstructions avoid unnecessary detail. The goal is not to create a portrait in the artistic sense, but to provide an informed approximation, a face that reflects anatomical reality without pretending to capture the individual's true appearance exactly. One of the most striking aspects of reconstructed faces of early humans is how familiar they can seem. The brow may be heavier, the face broader, the jaw more robust, but there is often something recognizable in the eyes, the general proportions, the sense of presence. This familiarity can be both comforting and unsettling. It reminds us that these were not abstract creatures but beings connected to us through deep evolutionary history. At the same time, reconstructions can reveal differences that challenge our assumptions. The face of Homo Rudolfensis, for instance, is broader and flatter than that of modern humans, with features shaped by a different diet and different patterns of muscle use. Seeing such a face helps us understand that the human lineage included a wide range of forms, not all of them resembling us closely. Reconstruction is not limited to faces. Scientists also attempt to estimate body proportions, posture, and movement. Limb bones provide information about height, weight, and locomotion. The shape of the pelvis suggests how individuals walked and how their bodies were balanced. Foot bones reveal details about gait and weight distribution. Combining all this information, researchers can create full-body reconstructions that show how a species may have looked standing, walking, or resting. These reconstructions are based on careful measurements and comparisons, but they are always presented with the understanding that they represent informed interpretations rather than exact replicas. Digital technology has transformed this process in recent decades. Three-dimensional scanning allows fossils to be studied and reconstructed without risking damage to the original specimens. Digital models can be manipulated, mirrored, and compared with other fossils in ways that were once impossible. Researchers in different parts of the world can examine the same digital skull, testing different reconstruction methods and sharing results. These advances have also improved the accuracy of facial reconstruction. Computer simulations can estimate muscle volume, simulate skin layers, and test how different assumptions affect the final appearance. While uncertainty remains, the range of possible appearances becomes narrower as methods improve. Still, there is an important balance to maintain. Reconstructions must remain grounded in evidence, resisting the temptation to fill gaps with speculation. The public often finds these faces compelling, and it is easy for artistic interpretations to drift toward dramatic or exaggerated features. Responsible scientists and artists work carefully to avoid this, presenting reconstructions as hypotheses rather than definitive portraits. There is also a philosophical dimension to reconstructing a lost face. A skull is a record of structure, but a face is also a record of life, expressions, movements, emotions. No reconstruction can capture the fleeting expressions that once animated those features, the subtle changes of mood, the individuality that every living being possesses, and yet, even a silent reconstruction can evoke a sense of connection. Looking at a reconstructed face of Homo Rudolfensis, one might feel a quiet recognition, an awareness that this being lived, struggled, and experienced the world in ways that were different from ours but not entirely alien. This sense of connection is part of what makes paleoanthropology so compelling. It bridges immense spans of time, bringing us face to face, in a sense, with individuals who lived hundreds of thousands or millions of years ago. It is also a reminder of how much remains unknown. Every reconstruction is provisional, subject to revision as new fossils are discovered or new techniques developed. A single additional skull can change our understanding of variation within a species. Improved dating methods can shift timelines. Advances in comparative anatomy can refine interpretations of muscle structure or posture. Science moves forward through this continual process of revision and refinement. Each reconstruction represents the best understanding available at the time, but never the final word. There is something quietly reassuring in this. Knowledge grows gradually through careful work and collaboration. The faces we see in museums and documentaries are not static truths, but steps along a path of discovery. Reconstructing a lost face also requires patience, not only from scientists, but from those who seek to understand the past. It is tempting to want clear, definitive answers, to imagine that we can know exactly what early humans looked like, how they spoke, what they felt. But the deeper we look into prehistory, the more we see that certainty is rare, and that understanding often comes in shades rather than sharp lines. And perhaps that is part of the beauty of this field. The past is not entirely recoverable, but it is not entirely lost either. Through fossils, fragments, and careful reconstruction, we can approach it gradually, respectfully, aware of both what we know and what remains beyond our reach. As we picture the faces of Homo Rudolfensis and their contemporaries, it becomes easier to imagine them not as distant abstractions, but as living beings moving through real environments, hearing real sounds, responding to the rhythms of their world. Sound leaves no fossils. Bones can be buried and preserved, footprints can harden into stone, tools can remain scattered across ancient ground, but the sounds of a world vanish the moment they are made. The calls of animals, the movement of wind through grass, the splash of water along a shoreline, all of these existed only in the present moment, heard and then gone. And yet, even though we cannot hear those sounds directly, it is possible to imagine them with some confidence, because the landscapes, the animals, and the behaviours that produce those sounds are known to us. If you were able to stand in East Africa during the time of Homo Rudolfensis, one of the first things you might notice would be that silence, in the sense we sometimes imagine it, did not really exist. There were quieter moments, certainly, but the environment was alive with noise, small, continuous sounds that formed a kind of background texture to daily life. Morning began gradually, not with sudden noise, but with a slow increase in activity. Before sunrise, the air would often have been relatively still. Insects that were active at night might still be moving, and the occasional distant call of a nocturnal animal might carry across the landscape. Then, as the sky began to brighten, birds would start to call, first one or two, then many, creating a scattered chorus that spread outward as more individuals woke and began to move. Bird calls served many purposes. Some signalled territory, others attracted mates, and still others warned of predators. To early humans, these calls were not merely background noise. They were information. A sudden burst of alarm calls from a group of birds could indicate the approach of a predator or the movement of a large animal through vegetation. Wind was another constant presence. In open grasslands, even a gentle breeze produces sound as it moves through stems and leaves. The sound changes with the strength of the wind and the type of vegetation. Short grass produces a soft, dry whisper. Taller grasses create a deeper, more continuous rustling. Leaves of trees move differently, producing irregular patterns of sound that shift as branches sway. For Homo Rudolfensis, these sounds were familiar and expected. A change in the pattern of wind or the sudden stillness of air might draw attention, because unusual silence can sometimes signal danger. Many animals become quiet when a predator is near, and the absence of sound can be as meaningful as sound itself. Footsteps were another part of the daily soundscape. Walking across dry ground produces a faint crunch or scrape. Moving through grass creates a brushing sound. On softer soil, footsteps may be nearly silent, while on gravel or rocky ground they become sharper and more distinct. Early humans likely learned to move quietly when necessary, placing their feet carefully, avoiding loose stones or dry branches that might snap under pressure. This skill would have been important not only for avoiding predators, but also for approaching animals when scavenging opportunities arose. The calls of mammals formed another layer of sound. Herd animals communicated with one another through low calls, snorts, and the sound of hooves moving across the ground. These sounds carried differently depending on the terrain. In open areas, they could travel long distances, especially in the cooler air of the early morning or evening. Predators also made themselves known through sound, though often less frequently. A distant roar or the call of a large carnivore could travel for kilometers, echoing faintly across the landscape. Such sounds would have been unmistakable, immediately drawing attention and perhaps prompting a group of early humans to move more cautiously or change direction. Closer at hand, smaller animals contributed their own voices. Monkeys and other primates called to one another from trees. Small mammals rustled in undergrowth. Lizards moved through dry leaves with quick, light sounds. Water had its own voice. Waves along the edges of lakes produced gentle, rhythmic sounds as they met the shore. In shallow areas, fish sometimes disturbed the surface, creating brief splashes. Rivers, depending on their size and speed, produced anything from a quiet murmur to a steady rushing noise. For a group approaching water, listening would have been an important part of staying safe. The sudden splash of a large animal entering the water, or the subtle disturbance caused by a crocodile moving beneath the surface, could signal danger. Rain, when it came, transformed the soundscape completely. The first drop striking dry ground produced a faint tapping sound, followed by the increasing intensity of a steady downpour. Rain on leaves creates a soft but continuous patter, and the smell of wet earth rises as dust settles. Storms could be dramatic. Thunder rolling across the sky, lightning striking trees or open ground, wind intensifying as clouds passed overhead. Such events were not daily occurrences, but they were part of the natural rhythm of the environment, and early humans would have experienced them without shelter, beyond what the landscape provided. Night brought a different set of sounds. As daylight faded, many birds grew quiet, but nocturnal animals became active. Insects produced continuous chirping or buzzing, creating a background hum that filled the darkness. Frogs called from near water, their voices carrying across still air. Predators often hunted at night, and their movements sometimes revealed themselves through sound. The rustle of grass, the sudden movement of prey, the distant call of an animal separated from its group. For early humans resting in sheltered areas, these sounds would have been both familiar and unsettling, reminders of the world beyond the small circle of safety provided by their group. Fire, which later became a central part of human life, would not yet have been a regular presence for Homo Rudolfensis. Without fire, nights were darker and quieter in certain ways, lacking the crackle of burning wood or the shifting sounds of embers. The darkness itself changed how sound was perceived. Without visual cues, the ear becomes more sensitive, and small noises seem larger and closer. Communication within groups likely involved a range of vocalizations. These were probably not structured language as we know it, but rather a system of calls, tones, and gestures. Soft sounds to maintain contact while moving, sharper sounds to signal alarm, variations in pitch or rhythm to convey urgency or reassurance. Even without complex speech, these vocalizations could carry meaning. Modern primates use dozens of distinct calls, each associated with specific situations or emotional states. Early humans almost certainly possessed similar abilities, perhaps with a greater capacity for variation and learning. Laughter, in a primitive form may have existed as well. Playful interactions among younger individuals or moments of social bonding often involve vocal expressions that resemble laughter in many primates. These sounds would have been brief but meaningful, reinforcing connections within the group. Breathing itself was part of the soundscape, especially during exertion. After a long walk under the sun, individuals would have rested, their breathing slowing gradually as their bodies recovered. The quiet rhythm of breathing shared within a group resting in shade was a sound of safety and calm. There were also moments when sound diminished. Midday heat often reduced activity among animals. Insects slowed, birds rested, and the landscape grew quieter, though never completely silent. These quieter periods may have provided opportunities for rest, for grooming, for simply sitting and observing. Sound shaped behaviour in subtle ways. The ability to distinguish between familiar and unfamiliar noises, to recognise patterns and notice changes, was an important skill. A sudden noise in the distance might prompt a group to pause and listen. A repeated sound could become a marker of location. The call of a particular bird near a water source, the sound of wind through a stand of trees that indicated a familiar route. Memory played a role here as well. Recognizing the usual sounds of a place made it easier to detect the unusual. Early humans likely developed a mental map not only of visual landmarks, but of auditory ones, places where certain animals were often heard, areas where wind moved differently, water that could be located by listening before it could be seen. It is interesting to consider how different this experience was from the modern world. Today, many of the sounds that surround us are artificial. Engines, machines, electronic signals, voices carried through speakers. The soundscape of early humans was entirely natural, shaped by wind, water, animals, and the movements of their own bodies. This does not mean it was always peaceful. Sudden noises could signal danger. Storms could be frightening. The roar of a predator at night would have been a powerful reminder of vulnerability. But alongside these moments were long periods of steady, familiar sound, the kind that becomes almost comforting through repetition. There is a certain calm in listening to natural sounds, a rhythm that does not demand attention, but supports it. For Homo Rudolfensis, these sounds form the background of every day, from waking to sleep, from childhood to old age. Over years and generations, individuals would have come to know their environment partly through sound, just as much as through sight or smell. The world was not only something to be seen and touched, but something to be heard, constantly, quietly, continuously. And while these sounds have vanished, replaced by the silence of stone and sediment, the evidence of the lives lived in that sound-filled world remains in other forms. Bones, tools, traces of movement, and the subtle changes in anatomy and behaviour that shape the course of human evolution. Understanding what their world sounded like helps bring us closer to seeing Homo Rudolfensis, not as distant figures in textbooks, but as living beings, surrounded by the same kinds of sensory experiences that shape our own lives: sound, movement, warmth, and the presence of others nearby. And as we continue to look at their lives in this way, another question begins to emerge, one that connects their existence to our own. What does the story of Homo Rudolfensis tell us about the broader story of humanity itself, and about the long path that eventually led to us? When we look at a name like Homo Rudolfensis, it can feel distant, almost clinical, like a label attached to a specimen in a museum drawer. But behind that name was a real population of living beings, individuals who woke under the same sun that still rises over East Africa, who searched for food, who moved carefully through landscapes filled with both opportunity and danger. And when we ask what Homo Rudolfensis means for our story, we are really asking something deeper. We're asking how humanity came to be what it is, and how many paths were explored before the one that led to us continued while others slowly faded. For a long time, people imagined human evolution as a ladder, a simple sequence of stages progressing steadily from primitive to advanced. In that picture, Each species replaced the one before it, moving step by step toward modern humans. It was an appealing idea because it was easy to understand. But discoveries over the past century, including fossils attributed to Homo Rudolfensis, have shown that the reality was far more complex. Instead of a ladder, the human story is closer to a branching network. Multiple species existed at the same time, each adapted to slightly different conditions, each experimenting in its own way with diet, movement, social life, and tool use. Some of those experiments continued, others ended. Homo Rudolfensis represents one of those paths, a lineage that was part of the early expansion of the genus Homo but did not persist into later periods. Recognizing this changes how we think about ourselves. It reminds us that modern humans are not the inevitable result of a single predetermined process. We are the outcome of many possibilities, most of which did not lead to the present. There is a quiet humility in that realization. It means that the traits we often consider uniquely human, our large brains, our languages, our cultures, were not guaranteed. They emerged gradually, shaped by countless small changes over immense spans of time, and they could easily have taken different forms or not appeared at all. Homo Rudolfensis also helps us understand how diversity played a role in human evolution. Diversity is not only a feature of ecosystems filled with different species of plants and animals, it is also a feature of our own lineage. Different early humans adapted to different environments, explored different strategies, and developed different combinations of traits. This diversity may have been a strength. When environments changed, some lineages were better suited to new conditions than others. The presence of multiple species increased the chances that at least one would survive and continue evolving. In this sense, Homo Rudolfensis was part of a broader evolutionary experiment, one of many attempts by nature to explore what a human-like creature could be. Another important lesson from Homo Rudolfensis is the gradual nature of change. When we look back across millions of years, it is easy to focus on milestones, the first stone tools, the first larger brains, the first migrations out of Africa. But these milestones were not sudden events. They were the result of incremental changes, small adaptations repeated over generations. The brain of Homo Rudolfensis was larger than that of earlier hominins, but still far smaller than that of modern humans. Their tools were simple, but they represented a significant step beyond the behaviours of earlier species. Their social lives were likely more complex than those of their ancestors, but still different from our own. In other words, they occupied a middle ground, not primitive in the sense of being undeveloped, but not yet possessing many of the traits that later defined humanity. This middle ground is where much of evolution happens, in transitions that are easy to overlook but essential to the larger pattern. Thinking about Homo Rudolfensis also invites us to consider how much of our identity is shaped by deep history. The ability to walk upright, to use tools, to learn from others, to adapt to changing environments, these traits did not appear suddenly in our species. They were built gradually over millions of years, carried forward by ancestors whose names we often do not know. In a sense, every step we take carries echoes of those earlier steps across ancient ground. There is also something meaningful in recognizing that Homo Rudolfensis was not alone in shaping our story. Evolution is not driven by individuals or even by single species, but by interactions among many forms of life and many changing environments. Climate shifts, geological processes, the movements of animals, the growth of plants, all influenced the conditions in which early humans lived and evolved. Our story is therefore not only a human story, but part of a larger narrative of life on Earth, a narrative in which countless species have appeared and disappeared, each contributing in some way to the world we inhabit today. Another perspective comes from considering how short recorded history is, compared to the time spans involved in human evolution. Writing has existed for only a few thousand years, agriculture for perhaps 10,000, cities for less than that. Yet Homo Rudolfensis lived nearly 2 million years ago. and even that is only a small portion of the history of life on this planet. This vast scale of time can be difficult to grasp, but it can also be calming. It reminds us that the present moment, with all its concerns and complexities, is part of a much longer continuum. The lives of early humans unfolded without knowledge of the future, just as ours do, and yet those lives contributed to a chain of events that eventually led to us. There is also a lesson here about resilience. Early humans faced challenges that were immediate and physical: hunger, predators, changing climates. Survival required cooperation, adaptability, and awareness. These qualities remain important today, though expressed in different ways. The story of Homo Rudolfensis also highlights the importance of curiosity and exploration, not only in the distant past but in the present. The scientists who study these fossils, who spend years analysing fragments and debating interpretations, are continuing a tradition of inquiry that is itself a defining human trait. The desire to understand where we came from is part of what makes us human, and yet even as we learn more, many questions remain unanswered. We do not know exactly how Homo Rudolfensis communicated, what their social structures were like, or how they experienced the world. The fossil record provides glimpses, not complete portraits. Perhaps that is part of what gives this field its quiet sense of wonder. There is always more to discover, more to understand, more pieces of the puzzle waiting beneath layers of sediment. Reflecting on Homo Rudolfensis can also change how we think about the present. When we see ourselves as part of a long continuum rather than as separate from nature, it becomes easier to appreciate the connections that link all living things. The air we breathe, the landscapes we inhabit, the rhythms of day and night. These are part of the same world that shaped our ancestors. Even the act of listening, of paying attention to the quiet details of the environment, is something we share with those early humans. Awareness of sound, movement and change was essential to their survival, and in a different way, awareness remains essential to our understanding of the world today. There is also something deeply human in the act of remembering. Fossils allow us to remember species that would otherwise be completely lost, to give them a place in the story of life. Homo Rudolfensis may be a forgotten ancestor in the sense that few people know the name, but through science their existence is remembered, studied and shared, and remembering shapes identity. Knowing that humanity has such deep roots, that our lineage extends back through countless generations of beings who lived in environments very different from our own, can foster a sense of perspective. It reminds us that change is constant, that adaptation is possible, and that the future, like the past, will be shaped by forces both large and small. When we look at a species like Homo Rudolfensis, so different from us in some ways and yet so clearly part of our lineage, how different were they really? And what does that comparison reveal about what it means to be human? At first glance, the answer seems obvious. Of course we are different. Modern humans build cities, travel across oceans and through the air, speak thousands of languages, and carry in our pockets devices capable of storing more information than entire libraries once held. Compared to that, a small group of Homo Rudolfensis walking along the edge of a lake nearly 2 million years ago might appear unimaginably distant, almost like beings from another world. But when the comparison moves beyond technology and begins to focus on the fundamentals of life, the differences become less absolute, and the similarities begin to emerge in quieter, more meaningful ways. To begin with, Homo Rudolfensis was a living human species, not in the sense of being identical to us, but in the sense of belonging to the same broader lineage, sharing anatomical features and behavioural tendencies shaped by common ancestry. They walked upright, used tools, formed social groups, cared for their young, and adapted to changing environments. These are not small things. They are foundations of what we recognise as human life. One of the strongest similarities lies in the rhythms of daily existence. Like us, they woke and slept, experienced hunger and satisfaction, felt warmth and cold, moved through landscapes with purpose, and depended on cooperation to survive. Their concerns were immediate and practical, finding food, avoiding danger, protecting the young, but beneath those concerns were emotional and social experiences that were likely familiar in many ways. Attachment, for example, is not a recent invention. Mammals form bonds with their offspring and with one another, and early humans were no exception. A parent carrying a child, an individual returning to the safety of a group after a day of searching for food, these are moments that resonate across time. Fear, too, was part of their lives. The presence of predators, the uncertainty of weather, the risk of injury. These created a world in which vigilance was essential. Modern humans still experience fear, though often in different forms shaped by different environments. Curiosity may also have been present. The ability to notice, to investigate, to try new behaviours is not unique to modern humans. Many animals display curiosity, and early humans, with their growing brains and flexible behaviours, likely explored their surroundings with interest as well as caution. This capacity for curiosity may have been one of the seeds from which later cultural and technological developments grew. There were, of course, real differences. The brain of Homo Rudolfensis was smaller than that of modern humans, and the structure of the brain was likely different in ways that influenced cognition. Language, as we know it, with complex grammar and abstract vocabulary, probably did not exist. Symbolic thought, the ability to represent ideas through art, writing, or mathematics, had not yet developed. These differences shaped how they experienced the world. Their understanding of time, for example, would have been tied closely to immediate events and natural cycles rather than to calendars or historical records. Their sense of identity would have been rooted in the group and the environment rather than in large-scale societies or nations. And yet, even here, the differences are not absolute. Modern humans still experience time through daily rhythms, waking and sleeping, eating and resting, moving through cycles that echo those of our ancestors. Our bodies and minds remain attuned to light and darkness, to hunger and fatigue, to the presence of others nearby. Another similarity lies in learning. Homo Rudolfensis did not attend schools or read books, but learning was central to their survival. Young individuals observed adults, practiced skills, made mistakes, and improved. Knowledge was transmitted through demonstration and imitation, a process that remains fundamental to human learning today. The tools they used were simple compared to modern technology, but the underlying principle was the same: recognizing a problem and finding a way to solve it using available materials. A sharp stone used to cut meat and a modern kitchen knife differ enormously in refinement, but both represent the application of thought and skill to meet a need. Social life also shows continuity across time. Humans are deeply social beings, and this trait has ancient roots. Cooperation, sharing, and communication were essential for early humans, just as they are for us. The scale has changed, but the basic patterns remain. It is also worth considering the sensory world they experienced. The warmth of sunlight on skin, the taste of fresh fruit, the sound of wind moving through grass. These sensations are timeless. The environments may differ, but the biological mechanisms of perception are shared. Pain, pleasure, fatigue, comfort. These experiences are part of being a living organism, and they connected Homo Rudolfensis to us more directly than any technological or cultural difference might suggest. There is another perspective that can be helpful. If a modern human infant were somehow raised in the environment of Homo Rudolfensis, without exposure to modern culture or technology, that child would grow up learning the same kinds of skills, observing the same landscapes, adapting to the same conditions. The brain and body of Homo sapiens would still differ in some ways, but the daily experience of life would be shaped primarily by environment and social context. This thought experiment highlights how much of what we consider uniquely modern is cultural rather than biological. At the same time, it is important not to overlook the real differences. Modern humans possess capacities for abstract reasoning, long-term planning, and symbolic communication that far exceed those of earlier species. These abilities have transformed the planet in ways that Homo Rudolfensis could not have imagined. But these capacities did not appear suddenly. They were built gradually, layer upon layer, over millions of years. The roots of our abilities lie in the behaviors and adaptations of early humans, including species like Homo Rudolfensis. In this sense, they were not so different from us, but rather part of the same unfolding process. There is also a psychological dimension to this comparison. It is natural to think of ancient humans as fundamentally other, to place a clear boundary between them and us. Doing so creates a sense of distance, but it can also obscure the continuity of human evolution. Recognizing similarities does not diminish the uniqueness of modern humanity. Instead, it enriches our understanding by showing how those unique traits emerged from earlier forms. It also encourages a sense of empathy across time. The individuals who belonged to Homo Rudolfensis were not statistics or specimens. They were living beings navigating a complex world, forming bonds, raising offspring, adapting to challenges, experiencing moments of calm and moments of fear. Their lives mattered to them in the same immediate way that our lives matter to us. This perspective can be grounding. It reminds us that humanity is not defined only by its most advanced achievements, but also by its basic patterns of living, patterns that extend far back into the past. When we ask whether we are really so different, the answer becomes more nuanced. In some ways, yes, our technologies, languages, and cultures have changed the scale of human life dramatically. In other ways, no. The core of what it means to be human, to move, to learn, to cooperate, to experience the world through a body and mind shaped by evolution, remains deeply connected to those who came before us. If Homo Rudolfensis was part of the long human dawn, one of many lineages that lived, adapted, and eventually disappeared, what does that long dawn itself look like when we step back and view it as a whole, the vast span of time in which humanity slowly emerged from its earliest beginnings? Night comes slowly in many parts of Africa. The heat of the day lingers in the ground, and the air cools gradually as the sun sinks below the horizon. Shadows stretch, colours soften, and the sounds of the day begin to fade into the sounds of evening. If you imagine a small group of early humans sitting together in such a moment nearly 2 million years ago, you begin to sense something that connects their lives to ours, not in the details of technology or language, but in the simple experience of being present as the world changes from day to night. That quiet transition is a fitting way to think about the long human dawn itself, not as a sudden beginning, not as a single turning point, but as a gradual brightening, a slow emergence of traits and behaviours that, over immense spans of time, would eventually shape what we now recognise as humanity. Homo Rudolfensis lived during one of the early phases of that dawn. They were not the first hominins to walk upright, and they were not the last to evolve larger brains or to use tools. But they were part of a crucial period in which many of the foundations of human life were being established. Mobility across open landscapes, flexible diets, growing social complexity, and the first quiet technologies that extended the reach of hands and minds. When we look back at this period, it is tempting to search for dramatic milestones. The first tool, the first fire, the first migration. Yet the deeper story is not about firsts, it is about continuity. Each generation inherited the world of the one before it, made small adjustments, learned new patterns, and passed those patterns on. The changes were often so gradual that no individual could have noticed them. Only when viewed across thousands of generations do the differences become clear. This is one of the most important lessons of the long human dawn. Evolution does not rush. It moves at a pace measured in lifetimes, in subtle shifts of anatomy and behaviour, in tiny variations that accumulate until they reshape a species. It is also a reminder that the human story is not a single line but a branching landscape. Homo Rudolfensis was one branch among many, part of a wider community of early humans who lived, adapted, and sometimes competed in the same regions. Some of those branches would eventually lead to later species. Others, like Homo Rudolfensis, would fade, leaving behind traces but no direct descendants that we can clearly identify. And yet, even those branches that did not continue played a role in shaping the conditions of the world that followed. They influenced ecosystems, competed with other species, and contributed to the diversity of the human lineage. In that sense, their lives were not isolated or insignificant. They were part of a larger process that connected all early humans, including those who would eventually give rise to us. Thinking about this long span of time can change the way we see the present. Modern life often feels fast, compressed, filled with deadlines and constant change. But the deeper rhythms of life on Earth move slowly. Continents shift, climates change, species evolve, and the processes that shape the world unfold over millions of years. Our own lives, brief as they are in comparison, are part of that larger flow. There is something calming in that realization. It does not diminish the importance of individual lives or the events of our time, but it places them in a broader context, one that extends far beyond the horizon of recorded history. The long human dawn was not only about physical changes, it was also about the gradual emergence of ways of living that still shape us today. Cooperation, for example, became increasingly important as early humans faced challenges that could not be solved alone. Sharing food, protecting the young, and learning from one another strengthened groups and improved survival. These behaviours did not appear fully formed. They developed slowly, influenced by the demands of the environment and the advantages of social living. Over time, they created the foundations of culture, not culture in the sense of art or literature, but culture as shared knowledge and behaviour passed from one generation to the next. Language, in its earliest forms, may have begun as simple vocalizations and gestures, gradually becoming more complex as brains grew and social interactions became more intricate. The ability to communicate effectively transformed human life, allowing knowledge to spread more quickly and cooperation to become more organized. Homo Rudolfensis lived before language reached the sophistication we know today, but they were part of the long process that made such communication possible. Another aspect of the human dawn was the changing relationship between humans and their environment. Early hominins were still deeply embedded in natural ecosystems, dependent on seasonal cycles and vulnerable to predators. Over time, as tools improved and knowledge accumulated, humans began to shape their environments more actively, altering landscapes, controlling fire, and eventually cultivating plants and domesticating animals. These developments were still far in the future during the time of Homo Rudolfensis, but the roots of those changes lay in the gradual increase in cognitive ability and behavioural flexibility that began much earlier. It is also worth reflecting on how fragile the path to the present may have been. If climate conditions had shifted differently, if certain populations had failed to adapt, if key traits had not emerged or spread, the human story might have taken a very different course. The survival of any lineage depends on a complex interplay of factors, many of them unpredictable. In that sense, the existence of modern humans is not the inevitable outcome of evolution, but one possibility among many. This perspective can foster a sense of humility. We are part of a lineage that survived not only through strength or intelligence, but also through adaptability, cooperation, and at times sheer chance. At the same time, there is a quiet continuity that links us to those early humans. The basic patterns of life, waking, moving, eating, resting, learning, forming bonds, remain the same. The settings have changed, and the scale of our activities has expanded enormously, but the underlying rhythms persist. If you listen carefully in a quiet place, you can still hear echoes of the world they knew, the sound of wind in trees, the rhythm of footsteps, the distant call of birds at dusk. These are sounds that have filled the lives of countless generations, long before cities or machines existed. Even the act of reflecting on the past, of wondering about the lives of those who came before us, is itself part of what makes us human. Curiosity about origins, about time, about the nature of existence, is a trait that has grown alongside our species. And perhaps there is comfort in that curiosity. It allows us to see ourselves not as isolated individuals in a single moment, but as part of a long, unfolding story, one that began millions of years ago and continues today. The long human dawn didn't end with Homo Rudolfensis, or with any other early species. It continued through the emergence of Homo erectus, through migrations across continents, through the eventual appearance of Homo sapiens and the development of language, art, and complex societies. Even now, in a sense, that dawn is still unfolding. Evolution has not stopped. Environments continue to change, cultures continue to evolve, and the human story continues to be written, not only in fossils and artifacts, but in the lives of people living today. As this journey through the distant past comes to a close, it is worth taking a moment to appreciate the scale of the story we have been exploring. Nearly 2 million years separate us from Homo Rudolfensis, and yet the connection remains unbroken. Every human alive today is linked through an unbroken chain of ancestors to those early populations who walked along the shores of ancient lakes, listened to the sounds of wind and animals, and lived lives shaped by the rhythms of a world both harsh and beautiful. That connection does not require us to know their names or their individual stories. It exists in our bodies, in our minds, in the simple fact that we are here at all. And as you rest, perhaps listening in the quiet of your own surroundings, you might imagine the long span of time stretching behind you. Countless generations, countless lives, each one a small part of a much larger story. A story that began long before memory and will continue long after any single lifetime has passed.